Tonight, I want to take you back not to a place, but to a moment so early that the universe hadn't even learned what distance meant yet. Not an explosion in the sky, but the gentle beginning of space itself, stretching open, carrying heat, light, and possibility outward like a slow, silent wave. Because everything you've ever seen, stars, oceans, mountains, the glow of city lights can be traced to that first hot, dense state and to the quiet cooling followed. And the most incredible part is that the universe still remembers it. There's a faint afterglow still filling the sky, a soft whisper of ancient light that has been traveling for nearly the entire age of time. So, if you're curious, if you've ever wondered how a universe can begin without a center, how light can outlive the moment it was born, and how tiny ripples became entire galaxies, stay with me. Before you fall asleep, leave a like, subscribe, or drop a comment, and let's drift together through the calmest, clearest truths we've learned about the Big Bang. The Big Bang model describes the universe as expanding from an early state that was extremely hot and dense, rather than describing an explosion occurring at a point in pre-existing space. In a simple way, that means the beginning is not pictured as a blast thrown outward into an empty room. Instead, the room itself, space, was part of what changed, growing and stretching from a much hotter and more compact condition. When scientists say hot and dense, they mean energy and matter were packed so closely together that the universe behaved like an intense, glowing ocean of tart, particles and radiation. As it expanded, it cooled, and the universe gradually became a place where atoms, light, and later stars could exist. The model is mainly a story of expansion and cooling, guided by measurable physics, rather than a single explosive event in a pre-made stage. In the Big Bang framework, space itself expands, meaning distances between faraway galaxies can grow, even if the galaxies are not moving through space in Tao. The usual sense. You can imagine this like a pattern drawn on a stretchy fabric. The pattern points can remain where they are on the fabric, while the fabric itself grows, increasing the distances between them. In cosmic terms, galaxies can be carried along by the expansion of space, so the separation between them increases over time. This is why astronomers talk about the expansion of the universe instead of galaxies flying away from a central point. The key idea is that the geometry of space changes, and that change shows up as growing distances across the cosmos. It is a quiet, steady stretching on the grandest scales. The universe's expansion is observed through the redshift of light from distant galaxies, where wavelengths are stretched as space stretches. Light travels as waves, and those waves have a wavelength like the distance between gentle ripples on water. When space expands while light is traveling, it stretches the light's wavelength, shifting it toward the red end of the spectrum. The farther the light has traveled through expanding space, the more it tends to be stretched. Astronomers measure this shift by looking at patterns in a galaxy's spectrum, like familiar fingerprints that appear moved to redder wavelengths. This redshift becomes a calm, reliable sign that space has been expanding during the light's long journey. The farther a typical galaxy is, the faster its recession speed tends to be, a relationship commonly summarized by Hubble's law. This means that, on average across the universe, more distant galaxies show larger redshifts, which we interpret as stronger recession due to expansion. It is not because those galaxies were pushed harder, but because there is simply more expanding space between us and them. Hubble's law gives a simple proportional relationship. Distance and recession speed rise together. This relationship is one of the clearest ways the universe reveals its large-scale behavior, like a steady rhythm in the background. And because it is measurable across many galaxies, it helps turn the Big Bang idea into a quantitative, testable model. The Big Bang model is primarily supported by three pillars: cosmic expansion, the cosmic microwave background, and the primordial abundance of light. Elements. The first pillar is the expansion we see through redshift and galaxy motion. The second is a faint glow that fills the sky, the afterlight of an early, hotter universe. The third is the specific mix of light elements, like hydrogen and helium, which matches predictions for a young universe cooling from intense heat. When these three lines of evidence align, they create a strong, calming consistency, as if three separate instruments are playing the same musical note. Together they form a foundation that can be checked and refined with new observations. This is why the Big Bang model remains the central framework for modern cosmology. The cosmic microwave background, or CMB, is a nearly uniform bath of microwave radiation, filling the entire sky. No matter where you point a sensitive microwave detector toward empty-looking space, toward distant galaxies, or between stars, you find this gentle purr, background glow. It is extremely faint, and it is remarkably even, like a soft, universal hum. This uniformity suggests it comes from a time when the universe was much more smooth and evenly distributed than it is today. Yet it is not perfectly uniform, and those tiny variations carry valuable information. The CMB is one of the most peaceful, steady signals we can measure from the cosmos, and it acts like a snapshot of the early universe. The CMB is interpreted as relic light released when the universe first became transparent to photons. Early on, the universe was so hot that light could not travel freely for long distances. Photons kept bumping into charged particles, scattering again and again, like trying to see through a thick fog. As the universe expanded and cooled, that fog thinned, and a time came when light could finally travel largely uninterrupted. The photons released at that moment have been traveling ever since, filling the universe and reaching us from all directions. Over billions of years, the stretching of space turned that once hot light into microwaves. So when we observe the CMB today, we are receiving ancient light that has been calmly drifting through space since the universe became transparent. Early in cosmic history, matter existed as a plasma of free electrons and nuclei that scattered light efficiently, making the universe opaque. A plasma is a state of matter where electrons are not bound to nuclei, leaving a mixture of charged particles. In that environment, light interacts strongly because charged particles easily scatter photons. This makes the early universe behave like a glowing, dense mist where photons cannot travel far without being redirected. It is a very different condition from the clear, transparent space we know today. The universe at that time was not dark, it was bright, but it was also not see-through. This early opacity is one of the reasons the CMB is so important. It marks the time when the universe transitioned from foggy to clear. When electrons combined with nuclei to form neutral atoms, light scattered far less, allowing photons to travel long distances freely. As the universe cooled, electrons slowed down enough to remain attached to nuclei, forming neutral atoms, mostly hydrogen and helium. Neutral atoms do not scatter photons as strongly as free charged particles do, so the fog lifted. In practical terms, the universe became transparent, and light could begin to stream across space in long, uninterrupted paths. The photons released then are the ones we still detect as the CMB. This moment is like the universe opening its eyes for the first time, letting light travel freely. It created a lasting background glow that now serves as a gentle record of early conditions. This transition is often called the epoch of recombination, even though it was the first time most electrons joined nuclei to form atoms. The word recombination sounds like something rejoining after being separated, and in a way, that's the idea. Electrons and nuclei were separate in the hot plasma and then came together as cooling allowed stable atoms. But historically, it was not a "re" in the everyday sense, because atoms had not existed before this point. Still, the term is used because it describes the process of electrons combining with ions. This epoch is crucial because it sets the time when the universe became transparent to light. It is also closely tied to the creation of the CMB as a freely traveling radiation field. The surface of last scattering refers to the time and place in cosmic history from which most CMB photons last interacted strongly with matter. Even though it is called a surface, it is not a physical wall or shell you could travel to like a planet. It is more like a boundary in time, a moment when the universe changed from opaque to transparent. The CMB photons we receive today mostly had their last major scattering event around that time. After that, they streamed through expanding space with only small later effects, like slight deflections from gravity. Thinking of it as a last scattering surface helps scientists model the CMB as coming from a particular era. It gives cosmology a kind of horizon line, a calm dividing point between earlier fog and later clarity. The CMB has an extremely precise blackbody spectrum, indicating it originated in a hot thermal environment. A blackbody spectrum is the smooth, specific shape of radiation you get when light and matter have reached thermal equilibrium, like the glow from a heated object. The CMB matches this pattern with remarkable accuracy, which strongly suggests it comes from a time when the universe was hot, dense, and well mixed. This is not a random mix of radiation. It has the signature of a unified thermal origin. Over time, expansion cooled this radiation, shifting it into the microwave range, but keeping its overall blackbody shape. That preserved shape is one of the strongest clues that the universe had a hot beginning. It is like a perfectly consistent thermal echo from very early times. Small temperature variations in the CMB across the sky encode information about tiny early density differences. Although the CMB is extremely uniform, it has small patches that are slightly warmer or cooler by tiny amounts. These differences correspond to early variations in density and motion in the primordial plasma. Warmer spots can reflect regions that were slightly denser or affected by gravitational potential differences, while cooler spots reflect slightly different Grell conditions. The variations are very small, far smaller than everyday temperature changes, yet they are measurable and meaningful. They form a delicate pattern that scientists analyze statistically. In that pattern, the early universe quietly recorded where matter was just a little more concentrated and where it was just a little less. Those early density differences later grew into galaxies, clusters, and the large-scale cosmic web. In the early universe, the differences were tiny, but gravity works patiently over time. Slightly denser regions pulled in more matter, growing denser still, while less dense regions became emptier by comparison. Over billions of years, this slow amplification created the large structures we see today: galaxies, groups of galaxies, huge clusters, and vast filaments connecting them. Between those filaments, enormous voids formed where matter is relatively sparse. This network-like arrangement is called the cosmic web. It is a calm example of how simple gravitational rules, given enough time, can sculpt a complex and beautiful large-scale pattern. CMB maps show a characteristic pattern of hot and cold spots that correspond to early sound waves in the primordial plasma. In the early universe, photons and ordinary matter were tightly coupled, behaving like a fluid that could support pressure waves. These waves are sometimes described as sound waves, though they are not sound in air. Rather, they are oscillations in density and pressure in a hot plasma. As they traveled outward, they created regions that were alternately slightly compressed and slightly rarefied. When the universe became transparent, these patterns were frozen into the radiation field we now observe. That is why the CMB has a textured appearance of tiny hot and cold patches. It is like a quiet imprint of ancient cosmic vibrations. These early sound waves produced a series of peaks in the CMB power spectrum, revealing details about the universe's contents and geometry. The CMB power spectrum is a way of describing how strong the temperature fluctuations are at different angular sizes on the sky. When scientists compute it, they see distinct peaks, which correspond to oscillations of different modes in the early plasma. The positions and heights of these peaks depend on how much ordinary matter exists, how much dark matter exists, and how space is curved or flat. In other words, the pattern is not just pretty, it is diagnostic. By fitting the peaks, cosmologists infer key properties of the universe. It is a gentle mathematical way the universe tells us what it contains and how it is shaped. The angular size of the main acoustic feature in the CMB strongly suggests that the large-scale geometry of space is very close to flat. If space was strongly curved, the same physical feature would appear larger or smaller on the sky, much like how a lens changes apparent size. The measured size of the main CMB feature aligns with predictions for a universe whose large-scale geometry is near Euclidean. This doesn't mean space has no curvature anywhere, but it does mean that on the largest scales we can measure, curvature is very small. It is like looking across a vast plain. Locally you might see hills, but over great distances it appears nearly level. This near flatness is one of the remarkable outcomes revealed by CMB observations. It provides a calm constraint on the overall shape of cosmic space. Flat in cosmology means the large-scale geometry is consistent with Euclidean geometry, not that the universe is a flat disk. It's easy to imagine flat as a sheet, but in cosmology, it is a statement about how geometry behaves over large scales. In a flat universe, parallel lines behave as in everyday geometry, and the angles of a large triangle add up close to 180 degrees in the hour. Appropriate cosmic sense. A universe can be flat and still extend in 3 dimensions in all directions. Flatness here refers to curvature, not to a pancake-like shape. This definition helps avoid common misunderstandings. It is simply a way of describing the broad geometry that best matches observations. The Big Bang model includes a time when the universe was so hot that atoms could not exist, because energetic photons would ionize them. Atoms depend on electrons staying bound to nuclei, but in a very hot environment, photons are so energetic that they knock electrons free. This keeps matter in an ionized state, the plasma, rather than neutral atoms. That is why stable atoms could not form until the universe cooled below a certain threshold. The early universe was too energetic for the gentle structure of atoms to remain intact. Only after expansion cooled the cosmos could electrons settle into stable orbits around nuclei. This is a simple, calming principle. Cooling allows complexity to form. As the universe expanded, its average temperature dropped, allowing new forms of matter to become stable over time. Expansion increases the volume available, spreading energy out more thinly. As energy density falls, temperatures decrease and conditions change in predictable stages. At very high temperatures, only certain particles and states can exist as it cools. Heavier particles become rare, nuclei can form, and later, atoms can form. Each step opens the door to a new kind of stability. This is why cosmologists can speak of epochs, each defined by what the universe could support. Over long time, this cooling by expansion created the conditions for stars, planets, and chemistry. It is an orderly unfolding driven by the gentle link between expansion and temperature. The overall cooling of the universe is a natural consequence of expansion. Photons lose energy as their wavelengths stretch. For light, energy is related to wavelength. Longer wavelengths mean lower energy per photon. As space expands, it stretches traveling light, making its wavelength longer. This redshifting steadily drains energy from the radiation field, lowering its effective temperature. It is not that photons slow down, they always move at light speed, but their wavelengths grow. Over billions of years, this process turned a once intensely hot radiation background into the cool microwave glow we detect today. The cooling is therefore built into the geometry of an expanding universe. It is a quiet, unavoidable consequence of stretching space. The Big Bang model is not a claim about what caused the universe to exist. It is a model for how the universe evolved from an early, hot, dense state. In science, a model can describe the behavior of something very well without fully explaining why it exists at all. The Big Bang model focuses on the universe's history after it was already in a hot, dense condition and began expanding. It tells us how temperatures changed, how light elements formed, and how structures grew. Questions about ultimate causes can move into philosophy, metaphysics, or theories not yet confirmed by evidence. Cosmology stays close to what observations can test and physics can describe. So the Big Bang model is best seen as a timeline of evolution, not a complete explanation of origin in the deepest sense. In many descriptions, time zero is a limit of the model rather than a fully described physical event. When scientists run the equations backward, densities and temperatures rise, and the mathematical description can approach a boundary where known physics may not apply. That boundary is sometimes labeled time zero, but it does not necessarily mean we fully understand what happened at that exact limit. It is more like the edge of a map, where the details become uncertain. New physics, such as quantum gravity, may be needed to describe conditions extremely close to that boundary. This careful wording helps keep cosmology honest about what is known and what is still open. The model is powerful, but it also has a frontier where understanding is incomplete. General relativity allows expanding universe solutions where space stretches uniformly on large scales. Einstein's theory of gravity does not only describe planets and stars, it can also describe the geometry of the entire universe. Under the assumption that the universe is broadly uniform, general relativity naturally leads to solutions where distances grow over time. These solutions don't require a center of expansion. Instead, they describe a general stretching of space everywhere. The expansion rate depends on what the universe contains, such as radiation, matter, and dark energy. This is why cosmology often treats expansion as a geometric feature, not as ordinary motion through space. The theory provides a calm mathematical backbone for the Big Bang picture. The Friedmann-Lemaitre-Robertson-Walker, or FLRW, metric is the standard mathematical description of a homogeneous, isotropic expanding universe. A metric is a way of describing distances and times in a curved and possibly changing spacetime. The FLRW metric is designed for a universe that looks roughly the same in all directions and places when averaged over huge scales. It includes a scale factor that grows with time, representing cosmic expansion. This framework lets scientists connect observations like redshift and distance with underlying cosmic dynamics. It is widely used because it matches the large-scale smoothness we observe. In a gentle sense, FLRW provides the coordinate grid on which the universe's expansion story is written. The Friedmann equations connect the expansion rate to the universe's energy components: radiation, matter, curvature, and dark energy. These equations are like a balance statement. The content of the universe influences how quickly space expands, and the expansion influences how densities change. Radiation contributes strongly in the early universe because it is energetic and abundant, while matter becomes more important later as expansion dilutes Kamai. Radiation faster. Curvature, if present, influences geometry and can affect the evolution of expansion. Dark energy, if it behaves like a cosmological constant, becomes increasingly important as the universe grows. By measuring how the universe expands, cosmologists infer how much of each component exists. These equations are a calm bridge between what we observe and what the universe contains. The Hubble parameter changes over cosmic time, and the Hubble constant refers specifically to its value today. The expansion rate is not fixed. It depends on the universe's contents and how those contents evolve with expansion. Early on, when densities were higher, the expansion rate was different than it is now. The term Hubble parameter refers to the expansion rate at any time, while Hubble constant is the special case of its current value. This distinction matters because different epochs follow different expansion rules. When astronomers talk about measuring the Hubble constant, they are trying to pin down the present-day expansion speed. Understanding it helps connect the early universe seen in the CMB to the later universe of galaxies and supernova. The Big Bang model predicts that the early universe produced mostly hydrogen and helium with very small amounts of other light isotopes. Hydrogen is the simplest and most abundant element, and in the early universe, it formed naturally as protons eventually captured electrons after cooling. Helium formed when protons and neutrons combined into stable nuclei during the earliest minutes. Only tiny traces of other light isotopes were produced, because conditions changed rapidly as the universe expanded and cooled. This leads to a universe that is chemically simple at the beginning. Later, stars create heavier elements through nuclear fusion, enriching the cosmos over time. So the Big Bang sets the initial chemical stage, mostly hydrogen and helium, with delicate traces of a few others. The creation of light nuclei in the early universe is called Big Bang nuclear synthesis, often shortened to BBN. Nuclear synthesis means making nuclei and in the Big Bang context it refers to the formation of atomic nuclei in the first few minutes. During that time, temperatures and densities were high enough for nuclear reactions to happen quickly. Protons and neutrons collided and stuck together in ways that produced deuterium, helium, and small amounts of other light nuclei. As the universe cooled further, those reactions slowed down and largely stopped. That is why BBN is an early, brief chapter in cosmic history. Its predictions are important because we can compare them with measurements of element abundances to test the Big Bang model. BBN occurred within the first minutes, when the universe was hot and dense enough for nuclear reactions to proceed efficiently. In those first minutes, particles were moving extremely fast, and collisions were frequent. That meant protons and neutrons had many chances to combine into nuclei. But the universe was also expanding quickly, and expansion reduces density and temperature over time. So there was a window where nuclear reactions were both possible and productive. Once the universe cooled enough, reactions could no longer keep up, and nuclear synthesis effectively froze out. This creates a predictable outcome, a particular mixture of light nuclei that remains as a fossil record. The briefness of BBN is part of its power, because it makes the predictions relatively clean and sensitive to a few key parameters. The predicted helium-4 fraction by mass is about 1/4 of ordinary matter, remarkably insensitive to many details. Helium-4 is especially stable, so when BBN got going, much of the available neutrons ended up locked into helium-4 nuclei. Because the neutron-to-proton ratio at that time falls into a certain range, the resulting helium fraction comes out to around 25% by E. Mass, for ordinary baryomic matter. This prediction is strong because it depends only modestly on many uncertainties. It is driven by fundamental nuclear stability and early conditions. Observational measurements of helium in low metallicity environments broadly support this result. The agreement gives confidence that the Big Bang picture captures something real about the early universe. It is a steady, reassuring consistency between theory and sky. BBN also predicts trace amounts of deuterium, helium-3, and lithium-7. Deuterium is a form of hydrogen with 1 proton and 1 neutron, and it is produced early but is also easily destroyed in stars. Helium-3 is a lighter isotope of helium that can be made in BBN and also in stellar processes, making it a bit more complex to interpret. Lithium-7 forms in small amounts, but its observed levels in certain old stars do not always match the simplest predictions, which is part of an ongoing puzzle. Still, the presence of these trace isotopes in predictable ranges is a key success of BBN. Their relative abundances depend on early universe conditions like baryon density. So these tiny traces act like a chemical whisper from the universe's first minutes. The abundance of deuterium is especially sensitive to the density of ordinary matter, making it a useful baryometer. If the early universe had more ordinary matter packed into it, nuclear reactions would have proceeded more efficiently, and deuterium would have been more thoroughly burned into helium. If there was less ordinary matter, more deuterium would have survived. This makes deuterium a sensitive indicator of baryon density. By measuring deuterium in environments where it has not been heavily processed by stars, scientists can infer how dense ordinary matter was during BBNT. This inferred density can be compared with CMB-based estimates, providing a strong cross-check. It's a gentle example of how a rare isotope can become a precise cosmic measuring tool. Heavier elements like carbon and oxygen were not made in meaningful quantities during BBN because the necessary stable nuclear stepping stones missing. Making heavier elements requires building up nuclei step by step, but early universe nuclear physics runs into a roadblock. Certain intermediate mass numbers do not have stable nuclei, which prevents an efficient chain of reactions from helium to heavier elements. The expanding universe also cools quickly, cutting off the time available for complex nuclear building. So the early universe produces light elements and then moves on, leaving heavy element creation to stars. This is why carbon, oxygen, and iron are products of stellar interiors and supernova, not the Big Bang's first minutes. The Big Bang sets the simple beginning, while stars later write the richer chemical story. The absence of stable nuclei with mass numbers 5 and 8 creates a bottleneck that prevents easy early formation of heavier elements. In nuclear terms, mass number counts protons and neutrons together. There is no stable nucleus with mass number 5, and none that stays stable at mass number 8 in the conditions of early nuclear synthesis. This means that when you try to combine helium-4 with a proton or neutron to form something heavier, the result tends to be unstable and quickly breaks apart. Without stable stepping stones, the path to building carbon and beyond is blocked. In stars, different conditions and multi-particle processes like the triple alpha reaction can bypass this, but the early universe doesn't have enough time. Density for that. So, this bottleneck is a quiet but powerful reason why the Big Bang made mostly light elements. It is a small detail of nuclear stability with huge cosmic consequences. Most elements heavier than helium were formed later inside stars and in stellar explosions, not during the Big Bang's first minutes. Stars act like long-lived furnaces that fuse lighter nuclei into heavier ones over millions or billions of years. In their cores, hydrogen becomes helium, and in more massive stars, fusion can proceed to form carbon, oxygen, and heavier elements up to iron. Elements heavier than iron are often formed in energetic events like supernova or neutron star mergers, where intense conditions allow rapid neutron capture. This means the universe's chemical richness is a layered history. First light elements from BBN, then heavier elements from generations of stars. Planets and life depend on these later stages because they require elements like carbon, oxygen, and iron. So the Big Bang provides the initial ingredients, and stars provide the later complexity. This is one of the most sweeping, calm connections between early cosmology and the material world around us. The Big Bang model also implies that the universe once had conditions far hotter than the cores of today's stars. A star's core is already an extreme place, with temperatures high enough to power nuclear fusion. Yet the early universe went far beyond that. In those earliest times, the entire universe was like a single, all-encompassing furnace, not confined to a star or a planet. When everything is that hot, matter behaves in unfamiliar ways, and the usual solid, liquid, gas categories don't apply. Instead, particles exist in high-energy states, colliding constantly, and many forms of structure simply cannot hold together. This idea helps explain why the early universe was simple in composition at first, and why complexity had to wait for cooling. In the earliest fractions of a second, known physics is pushed to extremes where quantum and gravity effects may both be important. Quantum physics describes the very small, while gravity shapes the very large, and the early universe brings those two realms together. At such enormous energies and densities, the smooth picture of space-time from everyday gravity may no longer be complete. At the same time, quantum uncertainty and fluctuations may play an outsized role in shaping what happens next. This is why the earliest instants are often described as a frontier, the place where our best theories are being asked to work in their most challenging conditions. Even so, the Big Bang framework remains useful because it clearly explains what comes after those earliest fractions of a second. Cosmologists often describe early times in epochs, based on which particles and forces dominated the universe's behavior. An epoch is like a chapter title that tells you what the universe was mainly made of and how it acted at that time. In one epoch, radiation might be the main driver, meaning light and fast-moving particles set the pace of expansion. In another epoch, matter becomes more important, allowing gravity to build structure more efficiently. These labels help scientists organize the story of the universe into understandable phases. They also help connect theory to observation, because different epochs leave different traces behind. It's a way of turning a vast timeline into a calm, readable sequence of conditions. The Planck epoch refers to times earlier than about 10^3 seconds, where a complete quantum theory of gravity would be needed for confident predictions. This is a time so early that our usual equations become uncertain, not because the universe did nothing, but because our tools are incomplete there. The Planck epoch is named after the Planck scale, where gravity may behave in a quantum way we do not yet fully understand. At this boundary, the concept of smooth space-time might break down into something more fundamental. Scientists treat it carefully, because it marks the limit where tested physics cannot yet describe every detail. Still, naming it helps clarify that the Big Bang story has a beginning where our knowledge becomes more tentative. After the Planck epoch, the universe may have entered a phase where known particle physics can begin to describe its contents more reliably. As the universe expanded, its average energy dropped, and conditions may have moved into a range where our current physics works better. This is like stepping from an unknown region of a map into territory where the landmarks are familiar. In these slightly later times, particles and forces can be discussed using established theories of high-energy physics, even if some details remain uncertain. This is where many early universe ideas become testable through later imprints, such as patterns in the cosmic microwave background. So while the very earliest boundary is mysterious, the universe quickly moves into a regime where we can make meaningful calculations. A key idea in many Big Bang models is inflation, a brief period of extremely rapid expansion in the earliest moments. Inflation suggests that for a very short time, space expanded at a dramatic rate, growing by an enormous factor. This does not describe galaxies flying outward like shrapnel, but rather space itself stretching very quickly everywhere. The idea is useful because it can explain several large-scale features of the universe in a single concept. It provides a mechanism for why the universe looks so smooth on huge scales, even though it contains small fluctuations. Inflation is not just added for drama, it is proposed because it helps solve specific puzzles about what we observe. Inflation was proposed to explain why the universe looks so uniform in temperature across regions that would otherwise seem causally disconnected. When we look across the sky, the cosmic microwave background is nearly the same temperature in all directions. Without inflation, some of those far-separated regions would not have had enough time to exchange signals or energy early on, which makes the uniformity harder to explain. Inflation offers a simple picture. Before inflation ended, regions that are now far apart were once close enough to come into balance. Then inflation stretched that balanced region to enormous size, making it appear uniform across the visible universe today. In that way, inflation acts like a smoothing process that happened early, leaving behind a calm sameness on the largest scales. Inflation also addresses why the universe's geometry appears so close to flat. In everyday experience, a small patch of a large sphere can look nearly flat if you zoom in close enough. Inflation works similarly, but on a cosmic scale. By stretching space so dramatically, it can make any initial curvature seem extremely small in the region. We can observe. This is one reason the universe's large-scale geometry, as measured by features in the CMB, looks close to Euclidean. Inflation provides a natural explanation for that near flatness without requiring extremely fine-tuned initial conditions. It turns, "Why is it so close to flat?" into "because it was stretched that way." This is a quiet example of how an early process can set a lasting, large-scale property. In inflationary scenarios, quantum fluctuations are stretched to cosmic scales, becoming seeds for later structure. Quantum fluctuations are tiny, unavoidable variations in fields and energy at very small scales. Inflation suggests that these microscopic variations were pulled outward and enlarged, so that they became macroscopic differences in density across space. Over time, gravity amplified those differences, leading to the formation of galaxies and clusters. This idea ties the smallest physics quantum behavior to the largest structures in the universe. It is one of the more striking links in cosmology, where the behavior of the very small can shape the arrangement of the very large. The result is a universe where today's structure may trace back to faint, early quantum ripples. The statistics of CMB fluctuations provide tests for inflation by constraining their distribution and scale dependence. Inflation does not just predict that fluctuations exist, it predicts specific patterns in how those fluctuations should behave across different sizes on double. The sky. Scientists analyze the CMB's temperature variations statistically, looking at how strong they are on large scales compared with small scales. They also look for whether the fluctuations follow the kind of distribution expected from simple inflation models. Because the CMB is such a clean early universe signal, it becomes a powerful testing ground for inflationary ideas. In this way, inflation moves from speculation toward evidence-based evaluation. The sky's faint pattern becomes a calm laboratory for testing early expansion scenarios. Measurements show the primordial fluctuations are close to scale invariant, meaning nearly similar strength across many length scales. Scale invariant means that if you look at the universe's early fluctuations on different sizes, their overall strength does not change dramatically from one scale to another. This is a specific, measurable property that many inflation models naturally produce. It implies that the early universe had a kind of balanced pattern of irregularities, not dominated by either only huge variations or only tiny ones. This balanced distribution helps explain why structure can form across many sizes, from galaxy scales to cluster scales. It is also one of the reasons inflation became compelling, because it matched what the CMB later revealed. The universe's early texture appears gently consistent across a wide range of scales. A slighted tilt in the fluctuation spectrum indicates small differences in strength between large and small scales, matching many inflation models. In practice, observations suggest the fluctuations are not perfectly scale invariant, but very close, with a small trend across scales. This tilt means one range of sizes has slightly stronger or weaker fluctuations than another. The existence of a tilt is important because it gives more detail than a perfectly flat spectrum would. It allows cosmologists to narrow down which inflationary models remain plausible, since different models predict different tilts. The tilt is subtle, but it is measurable, and it adds texture to our understanding of the early universe. It's a quiet refinement that improves the fit between theory and observation. Inflation can also dilute unwanted relics, like certain hypothetical heavy particles, by expanding the universe so drastically. Some theories of high-energy physics predict exotic particles or defects that might have been created in the early universe. If too many of these relics remained, they could conflict with what we observe today. Inflation offers a simple way to reduce their impact. By stretching space enormously, it spreads any relics out so thinly that they become rare or negligible in the paraff. Observable region. In this sense, inflation acts like a cosmic dilution process. It makes the universe cleaner and more uniform in what remains after inflation ends. This is another reason inflation is attractive. It can solve more than one early universe puzzle at once. Searches for primordial gravitational waves aim to find a distinct polarization pattern in the CMB known as BMOD. Gravitational waves are ripples in spacetime, and some inflation models predict a background of such ripples created in the earliest moments. If present, these ripples could leave a special twisting pattern in the polarization of the CMB, called BMOD polarization. Polarization is about the direction in which light waves oscillate, and the early universe can imprint patterns on that direction through scattering and gravitational paths. Effects. BMODs are especially interesting because they can be hard to produce in other ways at the largest scales. So scientists search carefully for this signature as a possible window into inflation's physics. The goal is to see whether the early universe left behind a faint gravitational wave fingerprint. Detecting primordial BMOD polarization would provide strong evidence for inflation's energy scale and dynamics. If a primordial B-mode signal were confidently measured and separated from other sources, it would support the idea that inflation occurred and would reveal information about how powerful it was. The strength of that signal is connected to the energy scale of inflation, offering clues about physics far beyond any laboratory capability. It could also help distinguish among different inflation models, since their predicted gravitational wave backgrounds differ. This is why B-mode searches are treated with great care and excitement. A detection would not just be a small detail, it would be a major window into the universe's earliest physical conditions. It would connect a subtle pattern in the sky to a profound early process. Current measurements place strong limits on how large the primordial gravitational wave signal could be. Even without a definitive detection, careful observations can still be very informative. By analyzing CMB polarization data, scientists can set upper bounds on the strength of primordial gravitational waves. These limits rule out some inflationary models that would produce too large a signal. In this way, the universe is still giving guidance. It is telling us what inflation could not have been, at least within certain model families. Such constraints help narrow the range of plausible early universe physics. Quietly, even a not yet seen result can shape the direction of cosmology. The Big Bang model distinguishes between radiation domination and matter domination, phases when radiation or matter controlled the expansion rate most. These phases describe which component of the universe's energy density mattered most for how the universe expanded. When radiation dominates, fast-moving particles and photons set the overall dynamics, influencing how quickly the scale factor grows. Later, when matter dominates, the universe's expansion responds more to the gravitational influence of mass in non-relativistic particles. This distinction is important because it changes how structure can grow and how distances evolve with time. It also helps explain why the early universe behaved differently from the later universe. Thinking in terms of domination eras gives a clear, calm way to organize cosmic history. In radiation domination, the energy density of photons and relativistic particles outweighed that of matter. Radiation energy density was enormous in the early universe because temperatures were extremely high and photons were abundant. Relativistic particles are those moving close to the speed of light, contributing energy in a way similar to radiation. Because radiation density drops quickly as the universe expands, this phase naturally ended as space grew and cooled. But while it lasted, it shaped the behavior of small fluctuations, since radiation pressure resists gravitational collapse. This means that in the radiation-dominated era, the universe expanded under conditions where light and fast particles were the main drivers. It is a foundational period that sets the stage for what comes next. In matter domination, the energy density of non-relativistic matter became more important than radiation. As the universe expanded, radiation thinned out and lost energy faster than matter did, allowing matter to take over the cosmic budget. Non-relativistic matter means particles moving much slower than light, so their energy is mainly in mass rather than motion. Once matter dominates, gravity has more opportunity to grow structures, because radiation pressure is less controlling. This era is crucial for the formation of galaxies and clusters, because it allows density differences to amplify more efficiently. It is during matter domination that the universe begins to look increasingly structured rather than smooth. The shift from radiation to matter domination is one of the major turning points in the Big Bang timeline. Today, the universe appears to be in a phase where dark energy significantly affects expansion, producing accelerated expansion on large scales. Observations indicate that the expansion of the universe is not merely continuing, but speeding up in a specific large-scale sense. Dark energy is the name given to whatever is driving this accelerated expansion, and in the standard picture, it becomes dominant at late times. This does not mean that galaxies are being pushed through space by a force like an engine. Rather, it means the expansion rate of space itself evolves in a way consistent with acceleration. The evidence comes from multiple probes, including supernova distances and patterns in large-scale structure. The result is a universe whose expansion history has changed over time, with a late-time push that becomes more important as the cosmos grows. It is a calm, gradual shift in the dominant component of cosmic dynamics. Dark energy is often modeled as a cosmological constant, but its physical nature remains uncertain. A cosmological constant is a simple way to represent dark energy as a constant energy density filling space. This model fits many observations well, and it has a clean mathematical form in general relativity. However, calling it a cosmological constant does not fully explain what it is physically or why its observed value is what it is. Some ideas treat dark energy as a property of the vacuum, while others explore slowly changing fields or modifications to gravity. At the moment, the cosmological constant model is the simplest widely used description, but it does not close the mystery. The uncertainty keeps dark energy as one of the most open questions in modern cosmology. The Big Bang model's timeline includes a moment when neutrinos stopped interacting frequently with other particles and began free streaming. Neutrinos are extremely light, weakly interacting particles that were abundant in the early universe. At very high temperatures, neutrinos collided and exchanged energy with other particles often enough to stay in thermal contact. As expansion pooled the universe, interaction rates dropped, and neutrinos began to travel long distances without many collisions. This transition is important because once neutrinos free stream, they behave like a background of nearly invisible particles that still influence gravity, expansion. They also affect how small fluctuations grow, because they can move out of dense regions more easily than heavier matter. In this way, even faintly interacting particles shape cosmic history through their collective presence. This event is called neutrino decoupling and occurred when weak interaction rates fell below the expansion rate. Decoupling means the neutrinos stopped being tightly coupled to the rest of the cosmic plasma. The weak force governs most neutrino interactions, and it is much weaker than electromagnetic interactions, which is why neutrinos are so elusive today. In the early universe, density and temperature made interactions frequent, but expansion steadily reduced collision opportunities. Once the universe expanded enough that neutrinos could no longer interact quickly compared to the pace of expansion, they effectively parted ways with the rest of tin quo, the plasma. From then on, they traveled freely, carrying information about early conditions, even though they are very difficult to detect. The timing of this decoupling is a key milestone in the particle history of the Big Bang. A cosmic neutrino background is expected to exist today, analogous to the CMB, but far harder to detect directly. Just as the cosmic microwave background is a relic sea of photons, the cosmic neutrino background would be a relic sea of neutrinos left over from the early CAS universe. These neutrinos would be everywhere, flowing through space and through us, largely unnoticed because they interact so weakly. Their existence is a natural prediction of the Big Bang framework, given how abundant neutrinos were in the early hot plasma. Detecting them directly is extremely challenging because their energies are expected to be very low and their interactions exceedingly rare. Still, their gravitational effects and their role in early universe physics are built into modern cosmological models. So even unseen, they remain an expected part of the universe's quiet background content. The predicted cosmic neutrino background temperature is lower than the CMB because neutrinos cool differently during early particle processes. Temperature in this context refers to the typical energy of particles in the background. Neutrinos decoupled earlier than photons, and later events like electron-positron annihilation heated the photon background more than the neutrinos. As a result, the neutrino background should be cooler than the CMB today. This difference is a subtle but important part of thermal history in the Big Bang model. It means that different relic backgrounds carry different cooling stories depending on when they decoupled and what later processes affected them. The predicted temperature relationship is an example of how carefully the early universe timeline can be reconstructed through physics. In the early universe, protons and neutrons could interconvert via weak interactions until cooling shifted the balance. Protons and neutrons are very similar particles, and the weak force allows processes that change one into the other under the right conditions. When the universe was hot enough, these conversions happened frequently, keeping protons and neutrons in a kind of dynamic balance. As the universe cooled, the reaction rate slowed, and the balance shifted toward more protons than neutrons. This matters because neutrons are needed to build helium and other light nuclei during nuclear synthesis. The changing balance sets the stage for how much helium could form later. It is a gentle reminder that the chemical outcome of the universe depends on timing, temperature, and interaction rates. As the universe cooled, neutrons began to decay more often than they were replenished, lowering the neutron-to-proton ratio. Free neutrons are unstable outside atomic nuclei and can decay into protons over time. In the early universe, when conversion reactions were frequent, neutrons could be replenished, but cooling reduced that replenishment. Once the universe became cool enough that interconversion slowed, neutron decay began to steadily reduce the neutron fraction. This decreasing neutron-to-proton ratio is one reason the helium fraction ends up around a quarter by mass rather than much higher. It also makes the timing of nucleosynthesis important. If nucleosynthesis happened much later, fewer neutrons would survive to form helium. So neutron decay adds a quiet urgency to the early nuclear timeline. The neutron-to-proton ratio set an important boundary condition for how much helium could form in BBN. Helium-4 requires 2 protons and 2 neutrons, so the available neutrons largely determine how much helium can be built. Because protons are more abundant after cooling, neutrons become the limiting ingredient. Once deuterium formation and subsequent reactions start, neutrons are quickly captured into helium-4 because helium-4 is very stable. This means a large fraction of surviving neutrons end up in helium. Therefore, the neutron-to-proton ratio acts like a dial that sets the final helium abundance. It is a simple relationship with a big outcome. How many neutrons survive determines how much helium the early universe makes. Deuterium formation was initially suppressed because high-energy photons could break deuterium apart, a bottleneck sometimes called the deuterium bottleneck. Deuterium is fragile compared to helium, and in the early hot universe, photons were energetic enough to destroy deuterium almost as soon as it formed. Even if protons and neutrons combined briefly into deuterium, a powerful photon could split it again. This prevented deuterium from accumulating, and without enough deuterium, heavier light nuclei could not form efficiently. Only when the universe cooled enough for deuterium to survive did nuclear synthesis proceed quickly to helium. This bottleneck shows how the early universe was governed by a balance between building and breaking. It is a calm example of how temperature controls what structures can persist. Once the universe cooled enough for deuterium to survive, helium and other light nuclei formed rapidly. When photons were no longer energetic enough to destroy deuterium easily, deuterium began to build up. That opened the pathway for further nuclear reactions, leading to helium-3 and especially helium-4. Because helium-4 is very stable, reactions quickly funneled available neutrons into helium-4 nuclei. This phase happened in a relatively short cosmic time because expansion and cooling continued, reducing reaction rates. The result is that the early universe locked in its light element mixture quite early. It is like a brief chemical sunrise. Once the conditions were right, the formation proceeded quickly before the universe cooled beyond the active range. The Big Bang model predicts that the CMB temperature should scale with cosmic expansion, getting hotter when looking back in time. As you look back toward earlier eras, you are looking at a universe that had a smaller scale factor and higher energy density. Since photon wavelengths stretch with expansion, reversing that expansion means the wavelengths were shorter in the past, corresponding to higher photon energies. This leads to a simple prediction. The CMB temperature increases in proportion to how much the universe has expanded since then. In other words, Earlier times correspond to a warmer radiation background. This scaling is a direct consequence of expansion, not a separate assumption. It provides a clear link between the CMB we measure today and the hotter conditions long ago. The CMB observed today is a cooled remnant of a much hotter radiation field from the early universe. The CMB did not start as microwaves. It began as radiation in a much higher energy form because the universe was far hotter at the time it was released. As billions of years passed, expansion stretched those photons into longer wavelengths, lowering their energies. The same light, traveling calmly through the growing cosmos, gradually shifted into the microwave part of the spectrum. That is why the CMB is sometimes described as the afterglow of the early universe. It carries the thermal shape of its origin, but at a much lower temperature now. This is one of the most direct, observable connections between today's sky and the universe's earlier heat. The observed average CMB temperature is about 2.7 Kelvin, reflecting billions of years of expansion and cooling. A temperature of a few Kelvin is extremely cold by everyday standards, close to the minimum energy environment found naturally in deep space. This low temperature is a consequence of how long the universe has been expanding since the CMB was released. The 2.7 Kelvin value represents the current leftover warmth of the early universe, stretched and diluted over cosmic time. Even at this low temperature, the CMB is measurable as a pervasive background signal. It is a quiet reminder that the universe still carries a detectable imprint of its earlier, far hotter state. The number itself becomes a calm landmark, the temperature of cosmic history still shining faintly today. CMB anisotropies are tiny on the order of tens of microkelvin compared to the average temperature. A microkelvin is 1/1,000,000th of a Kelvin, so these variations are extraordinarily small. Yet they matter because they encode the early universe's subtle density differences. The fact that the universe was so uniform, with only tiny variations, is itself informative. It means the early cosmos was smooth on large scales. At the same time, those small differences were enough for gravity to build the rich structures we see today. Measuring such tiny differences requires precise instruments and careful data analysis. The result is a detailed map of faint variations that act like a delicate fingerprint of early conditions. Those tiny fluctuations are a goldmine of information about cosmic composition and early universe physics. The pattern of fluctuations is not random noise. It has structure that reflects sound waves, gravity, and the mixture of matter and radiation. By analyzing how strong the fluctuations are at different angular scales, cosmologists infer the amounts of ordinary matter, dark matter, and other components. They can also test ideas about inflation, neutrinos, and the overall geometry of the universe. This makes the CMB a remarkably efficient source of knowledge. One sky pattern contains many cosmic parameters. It is like reading a single page that quietly contains the outline of the universe's early recipe. The more carefully we measure it, the more precisely we can describe the universe's ingredients and history. The Big Bang model implies that the observable universe was once filled with a nearly uniform particle soup. Early on, matter and radiation were mixed in a hot, dense state where particles collided constantly. In such conditions, any large differences in density would tend to smooth out, leading to a fairly uniform overall state. That is why the early universe is often described as homogeneous on large scales. This soup was not made of atoms and molecules like soup in a kitchen, but of fundamental particles and radiation in thermal motion. Over time, tiny variations remained, and those became seeds for later structure. But the baseline picture is a universe that began remarkably smooth and evenly distributed. As the universe expanded, gravity amplified small density differences, pulling matter into denser regions. Gravity is patient. It does not need large initial differences to create large outcomes over long time. If one region is slightly denser, it pulls in more matter, making it denser still, which strengthens its gravitational pull. Meanwhile, slightly less dense regions lose matter and become emptier in comparison. This runaway effect is how small, early irregularities can grow into galaxies and clusters. The expansion of the universe works alongside this process, influencing how quickly growth happens, but gravity remains the organizing force. In a calm way, the universe's structure is the long-term result of tiny beginnings slowly amplified by gravity. Dark matter, which interacts gravitationally but not strongly with light, plays a major role in structure formation. Dark matter does not emit, absorb, or reflect light in the way ordinary matter does, which is why it is dark to telescopes. But it does have gravity, so it can clump and form large halos that shape how galaxies form. Because it does not couple to radiation the same way baryons do, dark matter can begin clustering earlier without being held back by photon pressure. This makes it an essential scaffold for later structure. Ordinary matter then falls into the gravitational wells created by dark matter, forming stars and galaxies. So dark matter quietly shapes the universe's large-scale architecture while remaining difficult to observe directly. In the standard cosmological model, dark matter began clustering early, providing gravitational wells for ordinary matter to fall into later. In the early universe, ordinary matter was tightly coupled to photons, which created pressure that resisted collapse. Dark matter, by contrast, did not feel that same pressure, so it could start forming clumps sooner. These early dark matter clumps became halosa regions, where gravity is stronger because more mass is gathered. Once the universe cooled and atoms formed, ordinary matter could move more freely and begin to settle into these halos. Over time, gas collected in the centers of halos, cooled further, and formed stars. This sequence helps explain why galaxies form where they do. They often trace the invisible structure laid down by dark matter. Ordinary matter's interaction with radiation initially resisted collapse, delaying its full participation in structure growth until after recombination. When ordinary matter is coupled to photons, it behaves like a fluid under pressure, and pressure fights against gravitational contraction. This means that even if gravity tries to pull baryons into dense regions, radiation pressure can push back, smoothing things out. Only once the universe becomes neutral and photons decouple can baryonic matter respond more directly to gravity. This delay shapes when and how the first dense gas clouds form. It also means that the earliest structure growth is dominated by dark matter. The ordinary matter we see in stars and gas joins the process more fully only after the universe becomes transparent. After recombination, ordinary matter could fall more freely into dark matter halos, accelerating galaxy formation. Once neutral atoms formed, photons stopped pushing so strongly on matter, and baryons were less restricted by radiation pressure. This allowed gas to stream into existing gravitational wells created by dark matter. In these wells, gas could compress, cool, and eventually ignite star formation. That is one reason the period after recombination is so important. It unlocks the growth of visible structure. Over time, halos merge and grow, bringing gas along with them and building larger galaxies. The universe transitions from a smooth, glowing past to a clumpier, structured future, with recombination as a key turning point. The first stars formed when dense gas clouds cooled enough to collapse and ignite nuclear fusion. Star formation requires gravity to pull gas inward, but it also requires the gas to lose energy, or else pressure keeps it puffed up. Cooling mechanisms allow gas to radiate energy away, letting it compress further. Once a cloud becomes dense and hot enough in its core, nuclear fusion begins, and a star is born. The first stars likely formed in early dark matter halos where gas collected and cooled. These first stars changed the universe by producing light, heat, and later heavy elements. They also began to reshape the surrounding hydrogen through radiation, setting the stage for later cosmic transformations. The first generations of stars likely contained almost no heavy elements, since those elements had not yet been forged in prior stars. Heavy elements like carbon, oxygen, silicon, and iron are made inside stars and spread by stellar winds and explosions. Before stars existed, the universe was mostly hydrogen and helium, with only tiny traces of other light isotopes. That means the first stars formed from nearly pristine material. Such stars are sometimes called metal-free or extremely metal-poor, using metals in the astronomical sense. Their behavior, mass, and lifetimes may have differed from many stars today because heavy elements help gas cool and fragment during star formation. So the earliest stars are expected to be a distinct and important population in the universe's early story. The Big Bang model helps explain why the oldest known stars have extremely low metallicity, meaning low abundance of elements heavier than helium. If a star formed early, it formed before many generations of stars had time to enrich the galaxy with heavier elements. That means its chemical makeup reflects a more primitive universe. Astronomers measure metallicity by looking at spectral lines and comparing the relative amounts of heavier elements to hydrogen. Old, metal-poor stars are like living fossils, preserving evidence of the universe's early chemistry. Their existence fits naturally with a Big Bang universe that started with mostly hydrogen and helium. Over time, repeated cycles of star birth and death raise metallicity, so the oldest stars tend to stand out as chemically simple. The term metals in astronomy includes all elements heavier than helium, not just familiar metals like iron. This is a convention that can feel surprising at first, but it simplifies astronomical discussions. Hydrogen and helium are treated as the primary primordial elements, while everything else is grouped as metals because they were largely produced later and can T. Stars. So in astronomical language, oxygen and carbon are metals, even though they are not metals in chemistry class. This definition helps astronomers talk about how enriched a star or galaxy is compared with the early universe. Higher metallicity generally means more generations of stellar processing have occurred. It is a practical vocabulary that fits the Big Bang's chemical timeline. First light elements, then metals produced later. The Big Bang model implies that most hydrogen atoms in the universe are primordial, made long before stars formed. Hydrogen nuclei are simply protons, and after the early universe cooled enough, those protons eventually formed neutral hydrogen atoms by capturing electrons. Because hydrogen is the simplest element and was produced abundantly in the early universe, it remained the dominant element by number. Stars do burn hydrogen into helium, but the universe contains so much hydrogen that a vast amount remains unprocessed. This is why hydrogen gas still fills interstellar and intergalactic space. It is also why hydrogen plays a central role in star formation across cosmic history. In a quiet way, the universe is still filled with its earliest building block. Helium in the universe has both primordial origins and additional contributions from stellar fusion. A large fraction of helium was produced in the first minutes through Big Bang nucleosynthesis, forming a baseline helium abundance across the cosmos. Later, stars produced additional helium by fusing hydrogen in their cores, and they released some of that helium through winds or explosive events. So helium is both an early universe product and an ongoing stellar product. This dual origin means helium abundance reflects both primordial conditions and later stellar history, depending on where and how it is measured. In regions that have been heavily processed by stars, helium can be higher than the primordial fraction. But the key point remains. Helium's presence across the universe is one of the signatures of a Big Bang beginning, later supplemented by stellar activity. Deuterium is fragile and tends to be destroyed in stars, so its cosmic abundance generally decreases over time. Deuterium can form early in the universe, but it is easily burned into heavier nuclei when it enters hot stellar interiors. Unlike helium, which is built up in stars, deuterium usually gets consumed rather than produced in large amounts. That means deuterium is most informative when measured in environments but have not undergone much stellar processing. Over cosmic time, as more gas cycles through stars, deuterium tends to become less abundant. This makes deuterium a valuable tracer of early universe conditions because it preserves a memory of Big Bang nuclear synthesis when found in relativity. Pristine gas. Its fragility turns it into a kind of cosmic delicate marker that fades with stellar recycling. For that reason, measuring deuterium in pristine environments can be especially informative about early universe conditions. To learn about the early universe, scientists try to find gas clouds that have not been heavily enriched or altered by star formation. In such environments, deuterium is closer to its primordial abundance, making it a cleaner test of Big Bang nuclear synthesis predictions. By comparing observed deuterium levels with theoretical models, cosmologists infer the density of ordinary matter in the early universe. These inferences can then be checked against independent measurements from the cosmic microwave background. When these different methods agree, it strengthens confidence in the overall cosmic model. So deuterium, when found in the right places, becomes a quiet but powerful messenger from the first minutes of cosmic time. Lithium-7 is predicted by BBN, but observations in some old stars appear lower than expected, a discrepancy called the primordial lithium problem. In principle, Big Bang nuclear synthesis predicts a certain amount of lithium-7 should have formed in the early universe. But when astronomers measure lithium in the atmospheres of some very old, metal-poor stars, they sometimes find less lithium than the simplest models suggest. This mismatch is not a small curiosity. It has persisted long enough to be recognized as a real tension between prediction and observation. It could mean that lithium is being hidden or destroyed in stars in ways we do not fully account for, or that the early universe processes were slightly different than our simplest assumptions. The lithium problem is a reminder that cosmology is both successful and still incomplete in certain details. Even one element, present in tiny amounts, can raise deep questions about early physics. Possible lithium explanations include stellar depletion processes, systematic measurement effects, or new physics in the early universe. One possibility is that lithium in old stars does not reflect the original lithium content because lithium can be transported inside a star and destroyed in DAR, hotter layers. Another possibility is that measuring lithium is more difficult than it seems, with subtle effects in stellar atmospheres affecting the inferred abundance. A more radical possibility is that the early universe behaved differently, perhaps involving new particles or processes that altered lithium production. Each explanation has different implications, and researchers continue testing them with improved observations and models. This is how science often progresses. A small discrepancy becomes a pathway to better understanding. The lithium problem remains a calm, open question that invites careful work rather than quick answers. The Big Bang model predicts a specific relationship between CMB fluctuations and the amount of baryonic matter. Baryonic matter is the ordinary matter made of protons and neutrons, the stuff of atoms, gas, planets, and people. In the early universe, baryons interacted strongly with photons, and that coupling shaped the pattern of acoustic oscillations recorded in the CMB. Because of this, the amount of baryonic matter affects the relative strengths of features in the CMB's fluctuation pattern. By measuring these features, cosmologists infer the baryon density with impressive precision. This inferred density can then be compared with element abundance predictions from nucleosynthesis, creating a consistency check. In this way, the CMB becomes not only a picture of early light, but also a gentle scale for weighing how much ordinary matter exists in the universe. The heights and positions of the acoustic peaks in the CMB power spectrum quietly act like a measuring tool for the universe's baryon density. When the early universe was still a hot, charged plasma, ordinary matter and light were tightly linked, so they oscillated together like a springy fluid. The amount of baryonic matter changes how strongly that fluid could compress and rebound, which then changes the relative heights of the peaks we measure today. By carefully fitting those peak patterns, scientists can infer how much normal matter exists in the cosmos, even though we cannot scoop it up directly. It's a gentle example of how a subtle sky pattern becomes a precise cosmic scale. Those same peaks also constrain the dark matter density, because dark matter affects gravitational potentials and the way the early oscillations behaved. Dark matter does not join the photon baryon fluid the way ordinary matter does, but it still provides gravity, shaping the wells and hills that the fluid moves through. If there is more dark matter, the gravitational landscape is deeper, and that changes how the oscillations grow and how the peaks appear. So the peaks are not only telling us about ordinary matter, but also about the invisible mass shaping the universe from behind the scenes. This is one reason the CMB is so powerful. It encodes multiple ingredients at once. With careful analysis, those ingredients can be separated and estimated. CMB data also constrains the amount of extra radiation in the early universe, often summarized as an effective number of relativistic species. In simple terms, this is a way of asking whether, besides photons and the known neutrinos, there was any additional fast-moving, light-like energy content early on. Extra radiation would change how quickly the universe expanded during its early hop stages, and that would shift the detailed CMB pattern. Because the CMB is measured so precisely, even small changes in early expansion leave detectable fingerprints. Scientists express this with a parameter that acts like how many neutrino-like species were there, even if the extra component isn't literally a neutrino. It's a calm, indirect search for new physics using the universe itself as the detector. This effective number is especially sensitive to neutrino physics and to any additional light particles beyond the standard model. Neutrinos are naturally relativistic in the early universe, so their behavior contributes directly to the radiation budget. If neutrinos had unusual properties or if there were extra neutrino types, that could show up as a shift in this effective count. Likewise, hypothetical light particles, sometimes called dark radiation, could also add to the early energy density. The universe's early expansion rate responds to all of these possibilities, and the CMB records the consequences. So by constraining this number, cosmology quietly tests particle physics in a way that complements laboratory experiments. As the universe expands, the scale factor increases, and the temperatures of relic radiation drop inversely with that scale factor. The scale factor is a simple bookkeeping device. When it doubles, distances between faraway points double too. For radiation, expansion does two things. At Oneset spreads photons out, and it stretches each photon's wavelength, lowering its energy. Because of that, the temperature associated with the radiation background falls in a very orderly way as the universe grows. This relationship is one of the cleanest links between geometry and thermodynamics in cosmology. It helps explain why the early universe was hotter, and why looking back in time is also looking back into higher temperatures. The redshift parameter, often written as Z, expresses how much the universe has expanded since a given light signal was emitted. If Z is large, it means the light has been stretched a lot, which usually means it has traveled from a very early time. In practical terms, astronomers measure redshift by observing how familiar spectral patterns are shifted toward longer wavelengths. That shift becomes a convenient language for cosmic time and distance, letting scientists compare objects across the universe on a common scale. Redshift is not just a number, it's a quiet map coordinate for the universe's expansion history. By translating Z into distances and ages using cosmological models, we build timelines of how the cosmos changed. Recombination corresponds to a redshift of roughly 1,000, meaning the universe has expanded by about a factor of 1,000 since that era. This number gives a sense of scale. The universe was dramatically smaller, denser, and hotter when the CMB was released. A redshift near 1,000 also implies that the average wavelength of CMB photons has been stretched by about 1,000 times since then. That is why the CMB is microwaves today instead of visible light. This single redshift value is like a calm milestone marker on the universe's timeline. It tells you both how long ago and how much expansion separates us from that early transparent moment. The large-scale distribution of galaxies carries a subtle preferred separation scale, an imprint left by early universe sound waves. These are the same primordial oscillations that shaped the CMB peaks, but their influence didn't vanish after recombination. Instead, they left a slight enhancement in the probability of finding galaxies separated by a particular distance scale. Over cosmic time, galaxies formed within the matter distribution and inherited this faint pattern. It is not an obvious spacing you can see by eye in the night sky, but statistically it is measurable across huge surveys. This lingering imprint is a quiet memory of early plasma physics, written into the later cosmic structure. This feature is called Baryon acoustic oscillations, or BAO, and it acts like a standard ruler in cosmology. A standard ruler is a known physical length that can be used to measure cosmic distances by comparing how large it appears. BAO provides such a ruler because the early universe set a characteristic scale, the sound horizon that is predicted by physics and measured in the CMB. When that same scale is detected in galaxy clustering, it can be used to infer how the universe expanded between then and now. In this way, BAO turns ancient soundwave physics into a distance measuring tape. It is one of the calmest examples of cosmic consistency. The same scale appears in different eras and different kinds of data. BAO can be measured by analyzing how galaxy clustering changes with separation distance across large surveys. Scientists take enormous catalogs of galaxy positions and compute statistical measures like correlation functions or power spectra. Within those statistics, BAO shows up as a small bump or oscillatory feature at a characteristic scale. Because the signal is subtle, it requires many galaxies and careful control of observational biases. Yet when detected, it is remarkably useful because it is rooted in early universe physics rather than local astrophysical details. The measurement is a blend of patient observation and careful mathematics. It transforms the distribution of galaxies into a gentle record of the universe's expansion. BAO measurements help map the expansion history of the universe and constrain models of dark energy. By measuring the BAO scale at different redshifts, cosmologists can see how distances evolve over time. If the expansion history were different because dark energy behaved differently, for example, those measured distances would shift accordingly. So BAO acts as a set of checkpoints along cosmic time, showing how the stretching of space progressed. This is especially valuable because BAO is relatively robust against some of the complications that affect other probes. In combination with other measurements, it helps pin down the late-time acceleration of the universe. It's a quiet, geometric way to study one of cosmology's biggest mysteries. The sound horizon is the maximum distance those early sound waves could travel in the hot plasma before recombination ended their progress. Sound waves need a medium, and in the early universe, the photon baryon fluid served as that medium. But once neutral atoms formed and photons decoupled, that fluid changed character, and the driving pressure waves effectively stopped. The distant sound waves managed to travel by that time becomes a fixed scale imprinted in the universe. It is a horizon not of vision, but of pressure. Communication how far disturbances could spread. This distance is predictable from early universe physics, which is why it becomes such a useful ruler later. That sound horizon scale is imprinted both in the CMB and in the later distribution of matter. In the CMB, it shows up as the characteristic angular scale of the main acoustic feature. In the distribution of galaxies, it appears as the BAO scalar faint preference in galaxy separations. The fact that two very different observations, separated by billions of years, point to the same underlying scale is a deep consistency check. It means the universe kept a quiet memory of its early oscillations and carried it forward into structure formation. This dual imprint also helps cross-validate measurements, reducing reliance on any single method. It's like seeing the same watermark on two different pages of the universe's story. Comparing BAO scales at different redshifts allows scientists to infer how quickly the universe expanded at different eras. Because the physical ruler is set early, any change in the observed size of that ruler with redshift reflects how the universe's distance-redshift relation evolved. If expansion was slower or faster at a given epoch, the inferred distances would shift. This makes BAO a powerful way to trace expansion over a wide range of cosmic time. The method is especially valuable because it ties directly to early universe physics rather than complicated astrophysical brightness assumptions. By mapping BAO across redshifts, cosmologists build a calm, quantitative curve of cosmic expansion. Different observational methods can yield slightly different estimates of the present-day Hubble constant, a situation often called the Hubble tension. One set of methods uses the early universe, especially the CMB, to infer what the expansion rate should be today if the standard model is correct. Another set uses more direct, late universe measurements, like distance ladders anchored by nearby calibrators. The fact that these approaches do not perfectly agree may hint at small systematic errors, or it may suggest the standard model is missing something. Researchers treat it carefully because it is not just a disagreement about one number, it touches the connection between early and late cosmic history. The tension is a gentle but persistent puzzle in modern cosmology. CMB-based estimates infer the Hubble constant by fitting early universe physics and evolving it forward to today. In this approach, scientists measure the CMB's detailed pattern and infer parameters like matter density, baryon density, and curvature. Then, using a cosmological model, they compute how expansion should proceed over time, producing a predicted value for today's expansion rate. This method is powerful because the CMB is so precise and the early physics is relatively clean. But it relies on the assumption that the model used to evolve forward is correct. If some component like dark energy behavior or extra early radiation differs from the model, the inferred Hubble constant could shift. So this method is both a measurement and a test of the model's completeness. Distance ladder methods estimate the Hubble constant more directly using calibrated astronomical distance indicators. The idea is to build distances step by step. First calibrate nearby distance measures, then use them to calibrate brighter objects visible farther away, and so on. Common rungs include Cepheid variable stars and type ER supernova, which can act as standardizable candles. Once distances are known, the redshifts of galaxies in that distance range reveal the expansion rate. This approach is more local and less dependent on early universe modeling, but it is sensitive to calibration details and systematic uncertainties. Still, it provides an essential independent check on the universe's expansion today. Resolving the Hubble tension could require new physics, subtle systematics, or refined modeling of early or late cosmic processes. If the tension comes from measurement issues, then improving instrument calibration, dust corrections, selection effects, or modeling assumptions could bring methods into closer agreement. If the tension is real and not a systematic error, it might point toward additional early universe components, changes in dark energy behavior, or other extensions to the standard cosmological model. Researchers explore many possibilities, comparing multiple datasets and looking for consistent shifts. The goal is not to force agreement, but to understand what the universe is truly telling us. The tension remains a calm invitation to improve both observation and theory. The Big Bang model includes a period when electrons and positrons were abundant and could annihilate into photons as the universe cooled. At very high temperatures, energy could readily create particle-antiparticle pairs, so electrons and positrons existed in large numbers. As expansion cooled the universe, it became harder to create new pairs, and existing pairs more often annihilated each other. Their annihilation produced photons, adding energy to the radiation background. This event is part of the universe's thermal history, shaping how the photon bath evolved. It also helps explain why photons are so abundant today compared with baryons. The early universe, in this view, was a lively balance of creation and annihilation, gradually settling as it cooled. Electron-positron annihilation increased the photon background relative to neutrinos, affecting the thermal history. Neutrinos had already begun to decouple from the plasma around that era, so they did not share fully in the heating produced by electron-positron annihilation. Photons, still tightly coupled to charged particles, absorbed much of that energy, leaving the photon background warmer than the neutrino background afterward. This is why the predicted neutrino background temperature is lower than the CMB temperature today. It is a subtle but important distinction that comes from timing. Who was still interacting when the heating occurred? These details matter because they influence early expansion and the interpretation of cosmological parameters. The baryon to photon ratio is a key parameter that influences Big Bang nuclear synthesis outcomes and can be measured indirectly through cosmological Bantein observations. This ratio compares how many baryons, protons, and neutrons exist relative to how many photons exist. It matters because it sets how dense ordinary matter was in the early universe at a given temperature, which influences nuclear reaction rates during ED. Nuclear synthesis. A higher baryon to photon ratio means reactions proceed differently and leave different residual abundances of light nuclei like deuterium. The ratio can be inferred from CMB peak patterns and also constrained through BBN comparisons. It is a quiet bridge between particle counts and cosmic chemistry. That baryon to photon ratio is extraordinarily small, meaning there are vastly more photons than baryons in the observable universe. This can feel counterintuitive because baryons make the matter we touch, while photons feel intangible. But the universe is filled with photons, especially in the relic radiation backgrounds, and their total number is immense. The smallness of the ratio tells us that By number, the cosmos is dominated by radiation quanta, even though mass at late times is dominated by matter, dark energy. This also reflects the early thermal history, where photons remained abundant as the universe expanded. It's a gentle reminder that the invisible backgrounds of the universe can outweigh the visible matter in sheer count. The Big Bang model requires a mechanism that produced a slight excess of matter over antimatter, because otherwise they would annihilate almost completely. If the early universe began with equal amounts of matter and antimatter, then, as it cooled, they would have found each other and annihilated into radiation, leaving Gabbala behind very little matter. But the universe clearly contains abundant matter galaxies, stars, planets, so there must have been an imbalance, even if tiny, that favored matter. That small surplus would remain after most annihilation occurred, forming the material content of the universe today. This question is not about the expansion itself, but about the particle bookkeeping in the early hot phases. It is one of the most fundamental puzzles, why anything material remains at all. This challenge is known as baryogenesis, and multiple theoretical ideas compete to explain it. Baryogenesis is the general name for any process that creates a baryon asymmetry more matter than antimatter. Different proposals place baryogenesis at different times, such as during grand unification era processes, electroweak transitions, or through decays of heavy particles. Some ideas connected to neutrino physics through mechanisms like leptogenesis, where an imbalance in leptons eventually converts to an imbalance in baryons. What these ideas share is the need to produce a small but crucial excess of matter. Cosmology provides constraints because any successful mechanism must be consistent with observed abundances and the universe's thermal history. It remains a calm, active area where particle physics and cosmology meet. Sakharov conditions describe general requirements for generating a matter-antimatter asymmetry in the early universe. These conditions are not a specific mechanism, but a checklist of what any successful baryogenesis scenario must include. They help clarify why generating an asymmetry is not trivial in a universe that otherwise tends toward equilibrium. The conditions emphasize that ordinary symmetric physics will not automatically produce a lasting imbalance. By setting these requirements, Sakharov's framework guides theoretical work and helps researchers evaluate proposed models. It is a clean conceptual tool, a quiet set of rules for how the universe could end up matter-dominated. One Sakharov condition is baryon number violation, meaning processes must exist that can change the number of baryons. If baryon number were perfectly conserved in all circumstances, you could never generate more baryons than antibaryons overall. So baryogenesis requires that, at least under early universe conditions, some reactions can create or destroy baryon number. Certain extensions of particle physics naturally allow such processes at very high energies. Even within known physics, there are subtle effects that can violate baryon and lepton numbers under some conditions. This requirement makes baryogenesis a deep probe of fundamental laws. It suggests that early universe physics may have included reactions not commonly seen today. Another Sakharov condition is violation of C and CP symmetries, allowing matter and antimatter to behave differently. C symmetry roughly swaps particles with antiparticles, and CP symmetry combines that swap with a mirror flip of spatial coordinates. If these symmetries were perfect, matter and antimatter would behave identically, making it difficult to generate an excess of one over the other. CP violation is known to exist in certain particle processes, but the amount observed in the standard model may not be enough to explain the universe's large-scale matter dominance. This drives interest in additional sources of CP violation beyond what is currently confirmed. The early universe may have amplified such differences during certain transitions or decays. This condition highlights that tiny asymmetries in microphysics can have enormous cosmic consequences. A third Sakharov condition is departure from thermal equilibrium. So asymmetries are not washed out. In full thermal equilibrium, processes generally run forward and backward at matching rates, tending to erase net differences. To freeze in an asymmetry, the universe must go through conditions where equilibrium does not hold, such as rapid expansion, phase transitions, or the decay of heavy particles. When equilibrium is broken, reactions can leave behind a net surplus that cannot easily be undone. The early universe, with its changing temperature and expansion rate, naturally provides opportunities for such departures. This requirement ties baryogenesis to cosmic evolution, the timing and pace of expansion matter. It's another quiet link between large-scale cosmology and the smallest particle behaviors. The Big Bang model predicts that the early universe's temperature and density were high enough to keep many particle species in thermal equilibrium. In those early hot stages, particles collided frequently, exchanging energy and maintaining a shared temperature. This means the early universe can often be modeled like a hot fluid with a well-defined thermal state, at least until particular species decouple. As the universe cooled, heavier particles became rarer because producing them required too much energy, and many pairs annihilated or decayed away. This orderly dropping out of particle species is a major reason cosmology can be described in stages. Thermal equilibrium provides a calm baseline that makes predictions more tractable. Then decoupling events create distinct relic backgrounds and signatures. As temperature dropped, heavier particle species became rare and annihilated or decayed, leaving behind relic abundances. When the thermal energy of the universe falls below the mass energy needed to create a particle species, that species is no longer produced efficiently. Existing particles then tend to annihilate with antiparticles or decay into lighter particles. Depending on interaction strengths, some species can freeze out, leaving a leftover population called a relic abundance. This concept is central to many dark matter ideas, where dark matter could be a thermal relic from the early universe. Even when a species becomes rare, its disappearance can affect the energy budget and expansion rate at that time. The early universe is therefore a sequence of gentle transitions as different particles fade from dominance. The relic abundance of photons is enormous, making the universe photon-dominated by number, even though matter dominates mass at late times. Photons are massless and abundant, and the early universe created them in vast numbers through thermal processes and annihilations. As the universe expanded, photons remained numerous, even as their energies dropped. So even today, the universe contains an immense number of CMB photons. Meanwhile, matter dominates mass, because baryons and dark matter have rest mass that does not redshift away in the same way. This split many photons, but most mass in matter and dark energy is a subtle feature of cosmic bookkeeping. It reminds us that dominant by number and dominant by mass energy are different ideas in cosmology. The very existence of the CMB implies the universe once had a hot phase, because producing a cooled blackbody background across the whole sky is difficult to cull. Explain otherwise. A blackbody spectrum indicates that radiation and matter were once in close thermal contact, exchanging energy efficiently. That kind of equilibrium condition is naturally produced in a hot, dense early universe. As expansion cooled the radiation, the spectrum kept its blackbody form, becoming the CMB we observe today. Alternative scenarios historically struggled to reproduce such a uniform, precise thermal background without a hot beginning. The CMB is therefore not just an extra detail, it is a central clue that the universe passed through a hot, dense state. It is one of the calmest and most persuasive fingerprints of the Big Bang framework. Historically, Alternative models competed with the Big Bang, such as the steady-state theory, but the CMB strongly disfavored steady-state ideas. The steady-state view proposed that the universe looked the same not only in space but also in time, requiring continual creation of matter to maintain constant density during expansion. While that idea could address some observations known at the time, it did not naturally predict a cosmic background radiation with the CMB's precise properties. Once the CMB was discovered and its spectrum measured, the evidence strongly favored a hot, evolving universe. Over time, additional observations reinforced this preference, such as the pattern of light element abundances and large-scale structure growth. This historical shift shows how a single, well-measured signal can reshape scientific consensus. The CMB became a quiet turning point that anchored the Big Bang model. The uniformity of the CMB across the sky supports the idea that the early universe was close to thermal equilibrium on large scales. A near-uniform temperature suggests that energy was distributed very evenly, like a fluid that had time to mix thoroughly. Even though there are small variations, the overall smoothness is striking and meaningful. It implies that early conditions were not wildly chaotic from place to place, at least across the region that became our observable universe. This supports the use of simple cosmological models that assume large-scale uniformity. It also motivates ideas like inflation, which help explain how such uniformity could arise. The CMB's smoothness is therefore both a fact and a guide for theory. Small CMB temperature differences correspond to tiny fractional density differences, roughly 1 part in 100, 000 in the early bar. Universe. These differences are so small that, at first glance, it might seem impossible they could lead to today's galaxies and clusters. But gravity does not need large starting differences. It needs time. A region just slightly denser than average pulls in matter just a bit more effectively, and over billions of years, that small edge compounds into large structures. The early universe's smoothness tells us the starting point was gently perturbed, not violently uneven. Those tiny variations also allow precise modeling because they can be treated as small perturbations rather than messy turbulence. So the minute CMB differences are both a delicate imprint and the seed of everything structured we see. Those tiny differences were enough for gravity to eventually produce today's rich cosmic structure. The key is that the universe has had a very long time, billions of years for gravitational growth to operate. As matter flowed into slightly denser regions, those regions became more pronounced, leading to the formation of dark matter halos, then gas clouds, then stars, and galaxies. The process is gradual, with expansion setting the overall pace and gravity organizing the details. In this view, the universe is not built from dramatic starts, but from small beginnings patiently amplified. The existence of galaxies, clusters, and filaments is therefore consistent with an early universe that was almost smooth, but not perfectly so. It is a calm story of growth from subtlety. The Big Bang model includes a cosmological constant problem, where the observed dark energy density is far smaller than what simple quantum field estimates might suggest. In everyday terms, this is a mismatch between what some theories would naively expect for the energy of empty space and what we actually infer from cosmic AD. Acceleration. The universe appears to have a small but non-zero dark energy density, yet some calculations would predict something enormously larger. This gap is one reason dark energy remains deeply mysterious, even if a cosmological constant fits the data well. It is not just what is dark energy, but also why is it so small? In cosmology, that question sits quietly in the background of many discussions. The Big Bang model motivates very precise measurements of cosmological parameters such as matter density, baryon density, and the amplitude of primordial fluctuations. These parameters act like the knobs on the standard cosmological model, shaping how the universe expands and how structure grows. When scientists measure the CMB in galaxy clustering, they are not only collecting pretty maps, they are extracting numerical values that define the universe's recipe. Better precision helps distinguish between different physical possibilities, especially when results from different methods are compared. Over time, this has turned cosmology into a high-precision science, where small differences matter. The model becomes sharper as the parameter estimates improve. The parameter called sigma 8, written sigma 8, summarizes the typical strength of matter clustering on a particular scale and is constrained by CMB and galaxy surveys. You can think of sigma 8 as a way of describing how lumpy the matter distribution is when you smooth the universe over a specific large distance scale. A higher value means stronger clustering, with denser clumps and more contrast between regions. The CMB predicts how much clustering should develop over time, while surveys of galaxies and gravitational lensing observe clustering more directly in the later universe. Comparing these constraints helps test whether the standard model's growth history is consistent. Sigma 8 is therefore a compact way to connect early universe initial conditions to the structured universe we see now. Some measurements of clustering, often discussed using a related combination called S8, differ slightly depending on method, creating what is sometimes called an S8 tension. Different techniques like CMB-based inferences, weak lensing surveys, and galaxy clustering analyses do not always land on exactly the same preferred clustering strength. The differences are usually not huge, but they can be persistent enough to attract attention. If the mismatch is real and not just measurement systematics, it might hint at subtle changes in how matter grows under gravity or in the properties of dark energy, or neutrinos. If it is systematic, it may reflect how difficult it is to measure faint lensing signals or to model galaxies accurately. Either way, S-at-related discussions are a calm example of how precision cosmology tests itself. Cosmological tensions, like the Hubble tension or S8 tension, may point toward new physics or improved understanding of observational systematics. Sometimes a tension dissolves when measurements become cleaner or models become more careful. Other times, a tension becomes stronger and leads to a deeper discovery. In cosmology, many results depend on subtle calibrations, assumptions about astrophysics, and complex data pipelines. That makes it essential to compare multiple independent probes, rather than trusting only one. If the tensions persist across improved datasets, they may signal something missing from the simplest model. These puzzles are part of how the Big Bang framework continues to evolve and refine. The Big Bang model predicts that the CMB should exhibit slight polarization due to scattering processes in the early universe. Polarization is about the preferred direction of a light wave's oscillation, and certain kinds of scattering naturally create polarization patterns. When CMB photons scattered off free electrons, the geometry of the radiation field around those electrons could imprint a polarized signal. This polarization is faint, but it carries information that complements the temperature anisotropy map. It helps separate different physical effects, like density variations and velocity flows, and it improves parameter constraints. In a gentle way, polarization adds a second layer of early universe detail to the CMB. CMB polarization patterns help separate different physical effects and improve constraints on cosmological parameters. Temperature fluctuations alone already reveal a lot, but polarization provides additional handles on the physics. Certain polarization modes are linked to the motion of the plasma, while others reflect the pattern of density fluctuations and the geometry of scattering. By combining temperature and polarization data, scientists can reduce degeneracies, meaning fewer different parameter combinations can mimic the same SAR signal. Polarization also helps test reionization history and search for the faint signatures associated with gravitational waves. This makes CMB polarization a powerful tool, even though it is more challenging to measure precisely than temperature alone. Thomson's scattering of photons off free electrons is the key process producing much of the CMB polarization signal. Thomson's scattering is a low-energy form of electromagnetic scattering that occurs when light interacts with free charged particles, especially electrons. In the early universe, electrons were abundant and free before recombination, so photons scattered repeatedly. If the radiation field had a slight directional pattern at a given location, the scattering could generate polarization. This is why polarization carries information about the local conditions around the time of last scattering. The process is well understood in physics, which makes it reliable for interpreting CMB polarization patterns. It is a straightforward microscopic mechanism that creates a measurable cosmic scale imprint. The Big Bang model predicts a dipole anisotropy in the CMB, largely due to our motion relative to the CMB rest frame. The CMB appears slightly warmer in the direction we are moving and slightly cooler in the opposite direction, like a gentle Doppler effect. This dipole is much larger than the other intrinsic CMB fluctuations, but it is not mainly about early universe structure. Instead, it reflects the motion of the Earth, the Sun, and our galaxy relative to the frame in which the CMB is most uniform. Correcting for this dipole is a basic step in analyzing the deeper anisotropy pattern. It is also a strong confirmation that the CMB behaves like a real cosmic background with a meaningful rest frame. After accounting for the dipole, the remaining anisotropies reveal the intrinsic early universe fluctuations. Once we subtract the effect of our motion, what remains is the subtle pattern associated with the universe's early density and velocity variations. These are the fluctuations that encode the acoustic oscillations, the seeds of structure, and the statistical properties of primordial perturbations. The fact that we can separate the dipole cleanly from the intrinsic pattern is helpful because it makes the early universe signal clearer. It also shows that the largest CMB feature is local motion, while the fine texture is the universe's ancient imprint. This separation allows a calm, precise reading of the early universe. The Big Bang model suggests that cosmic expansion can be measured not only by redshifts, but also by time-based effects like time dilation in distant supernova light curves. In an expanding universe, signals from distant events appear stretched in time by a factor related to redshift. For supernova, this means the brightening and fading of the explosion's light curve takes longer when observed at high redshift. This time stretching is not because the supernova itself is slower, but because the expansion stretches the time intervals of the arriving photons. Observing this effect provides an additional, independent confirmation of expansion. It is a gentle way the universe reveals expansion through time, as well as through wavelength. Type IR supernova serve as standardizable candles that helped reveal accelerated expansion at late times. Type EAA supernova have a characteristic brightness pattern that can be calibrated, allowing astronomers to estimate their distances from how bright they appear. By comparing those distances with redshifts, scientists discovered that distant supernova were dimmer than expected in a decelerating universe, implying that expansion has been accelerating. This was a major turning point that introduced dark energy as a key part of the standard cosmological model. The result has been supported by multiple other probes, but supernovae were central in revealing it. They act as bright, reliable markers scattered through cosmic time. The discovery of late-time accelerated expansion introduced dark energy as a major component of the standard cosmological picture. Once acceleration was inferred, cosmologists needed an explanation that fits within general relativity or modifies it in controlled ways. Dark energy became the name for whatever component causes expansion to speed up on large scales. In the simplest model, dark energy behaves like a constant energy density, but other possibilities exist. The key point is that acceleration is not a small effect. It has shaped the recent history of the universe. This changes how we project the universe's future and how we interpret distance measurements. Dark energy is now a foundational element of the Big Bang model as it is used today. The Big Bang model implies that the universe's expansion rate was faster in the past when densities were higher. In general relativity, higher energy density leads to stronger gravitational influence on expansion dynamics. Early on, radiation and matter densities were much larger because the universe was smaller and more compact. As expansion increased volume and cooled radiation, those densities dropped. This naturally changes the expansion rate over time, even without any exotic assumptions. It is part of why the Hubble parameter is time-dependent. The universe's expansion history is therefore a curve, not a single fixed speed. During radiation domination, the scale factor grows roughly as the square root of time in simplified models. This relationship comes from solving the Friedmann equations when radiation is the dominant energy component. It means that at very early times, the universe expands in a particular predictable way, fast at first, then gradually slowing in the sense of how the scale factor changes with time. The exact behavior depends on assumptions like perfect uniformity and the composition of radiation, but the square root trend is a common reference. This era is important because it sets how horizons grow and how early perturbations evolve. It is one of the clean mathematical chapters of early cosmic expansion. During matter domination, the scale factor grows roughly as time to the 2/3 power in simplified models. When matter dominates, the expansion slows differently compared to radiation domination because matter's density scales with volume dilution, but not with photon redshift energy loss. The 2/3 power law captures that different scaling. This era is especially important for structure growth because gravity can amplify perturbations more efficiently once matter dominates. In practice, the real universe transitions between eras, but this simple law is a useful guide. It provides an intuitive picture of how expansion behaves when mass in matter is the main driver. It is a calm, predictable pattern emerging from the equations. With the cosmological constant dominating, expansion approaches exponential growth in the far future. If dark energy behaves like a true cosmological constant, its density stays constant even as the universe expands. As matter and radiation dilute away, the constant component becomes increasingly dominant. In that regime, the scale factor grows more and more rapidly, approaching exponential behavior. This does not imply galaxies nearby are being torn apart, because local gravitationally bound systems can remain stable. It does imply that on very large scales, distances between unbound regions grow faster over time. This is one of the simplest projections for the universe's long-term expansion, if the cosmological constant model is correct. The Big Bang model predicts that the CMB temperature should be higher in the past, and observations of certain systems can test this temperature evolution. Because the CMB temperature scales with the expansion, it should increase as 1 plus z when you look back to earlier times. Astronomers can sometimes test this by studying the excitation of certain atoms or molecules in distant gas clouds, where the CMB contributes to the population of energy levels. By comparing those populations at different redshifts, they can infer an effective background temperature. Such measurements are challenging and require careful interpretation, but they provide a direct check on the expected temperature scaling. This offers another calm consistency test of the expanding universe picture. The Big Bang model treats the early universe as a natural laboratory for high-energy physics, beyond what humans can build on Earth. Particle accelerators can reach impressive energies, but the early universe reached conditions far beyond any laboratory. This means early cosmology can, in principle, reveal hints of particle properties that are otherwise inaccessible. Things like neutrino behavior, hypothetical light species, and the dynamics of early fields can all leave subtle imprints in the CMB and large-scale structure. The laboratory here is not controllable, but it is vast and informative. By measuring relic signals, we learn about physics at energies we cannot reproduce directly. It is a quiet, indirect partnership between astronomy and particle physics. Constraints on neutrino masses arise partly because neutrinos affect how structure grows and how the CMB looks. Neutrinos, even with small masses, move quickly and can spread out rather than clump on small scales. This behavior changes the growth of matter perturbations, subtly smoothing structure at certain scales. In the CMB, neutrinos also influence the early expansion rate and the evolution of gravitational potentials, affecting the anisotropy pattern. By comparing detailed cosmological observations with theoretical predictions, scientists can place upper bounds on the sum of neutrino masses. These constraints complement laboratory experiments that measure neutrino mass in other ways. Cosmology thus becomes a calm tool for weighing particles that are otherwise extremely difficult to measure. Even small neutrino masses suppress structure on some scales by free streaming out of overdensities. Free streaming means neutrinos travel long distances without being trapped by gravity in small potential wells, especially when they are still moving very fast. If neutrinos have mass, they eventually slow down, but their early fast motion can still reduce the amount of clustering that would otherwise occur. This suppression is scale-dependent, affecting smaller structures more than larger ones. Observationally, that means certain patterns in galaxy clustering and lensing can reveal the influence of neutrinos. It's a subtle effect, but modern surveys are sensitive enough to care about it. This is another example of how tiny particle properties can influence the shape of the cosmos. The Big Bang model predicts a relationship between baryon density and the relative heights of certain CMB peaks. Because baryons add inertia to the photon-baryon fluid, they change how strongly the fluid compresses in gravitational wells compared to how it rarefies. This creates a pattern where some peaks are enhanced relative to others depending on baryon content. By measuring the peak ratios, cosmologists infer baryon density in a way that is largely independent of local astrophysics. This inferred value can then be checked against primordial element abundance measurements from Big Bang nucleosynthesis. The agreement between these methods is one of the model's most soothing internal consistency checks. It is as if two different cosmic records are telling the same story. The second and third acoustic peaks are particularly informative about the baryon to dark matter ratio. Different peaks respond differently to the balance between baryons and dark matter because dark matter shapes gravitational potentials, while baryons participate directly in the oscillations with photons. The detailed pattern how high one peak is relative to another encodes this balance. By fitting these features, scientists extract the relative contributions of visible baryons and invisible dark matter. This is remarkable because it means the sky's faint microwave texture reveals the unseen matter budget. It also means the early universe provides a cleaner environment for measuring these ratios than the later universe, where messy astrophysics complicates things. The peaks become a calm decoding key for cosmic composition. The Big Bang model implies that photon diffusion in the early universe damped small-scale CMB anisotropies, an effect called silk damping. In the hot plasma, photons scatter often and undergo a kind of random walk. Over time, this diffusion allows photons to leak out of small, overdense regions, smoothing out temperature differences on very small scales. The result is that the CMB has less contrast at tiny angular scales than it would otherwise. This effect is not a flaw in the data, it is a predictable physical process that helps confirm the plasma picture. It also provides information about conditions like the thickness of the last scattering surface. Silk damping is a gentle smoothing filter created by the early universe itself. Silk damping arises because photons random walk out of overdense regions, smoothing fluctuations on small scales. If you imagine a crowded room where people bump into each other constantly, no one can travel in a straight line for long. Photons in the early universe behaved similarly, scattering repeatedly off electrons. This means they gradually drifted from hotter or denser areas into cooler or less dense ones. That drift reduces sharp contrasts, especially over small distances, because diffusion is more effective at erasing small features than large ones. When the universe became transparent, the remaining pattern carried this diffusion imprint. The damping tail of the CMB spectrum is therefore a quiet record of photon travel in a foggy plasma. The Big Bang model predicts that gravitational redshifting and time-evolving gravitational potentials imprint additional CMB anisotropies. Light climbing out of gravitational wells loses energy, which appears as a redshift, and this can affect the observed temperature pattern. If gravitational potentials change while the photon passes through them, the photon can gain or lose energy in a way that leaves a distinctive imprint. These effects add to the primary anisotropies created at last scattering. They show that the CMB is not only a snapshot of one moment, but also a backlight that has interacted with large-scale structure over time. This makes the CMB a layered signal, part early imprint, part accumulated journey. It quietly carries information about both the early universe and the later distribution of matter and energy. The integrated Sachs-Wolf effect occurs when CMB photons pass through gravitational potentials that change over time, often due to dark energy. If a gravitational well deepens or shallows while the photon is inside, the photon's energy shift on entering and leaving does not cancel perfectly. In a universe dominated by matter with stable potentials, the effect is small. But when dark energy becomes important, large-scale potentials can evolve. This creates a subtle temperature correlation between the CMB and the large-scale distribution of galaxies. Detecting it is challenging because the effect is weak, but it provides evidence that expansion dynamics at late times influence gravitational potentials. The integrated Sachs-Wolf effect is a quiet way dark energy touches the CMB. The early Sachs-Wolf effect reflects gravitational redshifts at the time of last scattering. At recombination, photons were released from regions with slightly different gravitational potentials. A photon emerging from a deeper gravitational well loses a bit more energy climbing out, appearing slightly cooler, while photons from shallower regions appear slightly warmer. This contributes to the large-scale temperature variations in the CMB. It ties the observed anisotropy directly to the early universe's density field and space-time curvature. The effect is part of why the CMB temperature map is such a direct probe of early gravitational potentials. It is a calm imprint of gravity on ancient light at the moment the universe became transparent. In the early universe, ordinary matter was tightly coupled to radiation, so baryons were shaped by the push and pull of light. Photons carried pressure, and because baryons were interacting constantly with those photons, the combined mixture behaved like a single fluid. When gravity tried to compress a region, radiation pressure pushed back, creating rhythmic oscillations rather than immediate collapse. This is why the early universe did not instantly fragment into clumps of ordinary matter, even though gravity was present. The coupling between photons and baryons acted like a supportive cushion, resisting sharp density growth until the universe cooled enough for atoms to form. After decoupling, when photons stopped strongly dragging baryons around, ordinary matter could begin to grow under gravity much more directly. The moment neutral atoms formed, radiation pressure lost much of its grip on baryons, and the brakes on collapse loosened. Baryons could then fall into existing gravitational wells, especially those formed earlier by dark matter. Over time, this made the distribution of ordinary matter look increasingly similar to the underlying dark matter pattern. Gas gathered, cooled, and became dense enough to form stars, turning invisible gravitational structure into luminous galaxies. In this way, decoupling marks a quiet shift from a pressure-dominated early behavior to a gravity-dominated growth of visible structure. The Big Bang model helps explain why the universe's large-scale structure looks filamentary, with dense nodes connected by strands and huge voids between them. When you map galaxies across the sky, you don't find an even sprinkling, you find a web-like pattern. Dense regions appear like intersections, filaments connect them like cosmic highways, and in between there are immense, underdense voids. This arrangement is not random decoration. It is what gravity naturally produces when it amplifies tiny initial fluctuations over billions of years. The early universe started nearly smooth, and gravity pulled matter into elongated structures that grew more prominent with time. The result is a cosmic architecture that looks like a network, formed calmly from simple beginnings. This cosmic web arises naturally from gravitational growth starting from near-Gaussian initial conditions. Gaussian here means the initial fluctuations were distributed in a statistically simple way, like many small random variations rather than a few extreme Breuer lumps. When such a field evolves under gravity, it tends to form filaments and nodes because matter flows along gradients toward denser regions. The geometry of collapse is not only spherical, it can be sheet-like and filament-like, depending on how the initial irregularities are shaped. Over time, these flows carve out voids and concentrate matter into connected structures. The web is therefore a predictable outcome of gravitational evolution, not something added by hand. Cosmological simulations that begin with Big Bang-style initial conditions reproduce many statistical properties of observed galaxies and clusters. Scientists run large computer simulations where they start with early universe fluctuations consistent with the CMB and then let gravity evolve the matter forward in time. As the simulation progresses, halos form, merge, and build the scaffolding for galaxies and clusters. When the results are compared with real surveys, many broad features match, such as clustering strength, filament void patterns, and large-scale correlations. This doesn't mean every detail is perfect, because galaxy formation involves complicated gas physics, but it does show the Big Bang framework captures the essential gravitational backbone. The ability to reproduce real cosmic patterns from early conditions is a calm and powerful validation. The Big Bang model implies that the earliest massive structures formed from rare, unusually high peaks in the initial fluctuation field. In a mostly smooth early universe, most regions had only slight over- or underdensities. But statistically, a few regions were higher than average by a larger margin rare peaks. Those rare peaks had a gravitational advantage. They began collapsing earlier and more strongly, helping them form the first massive halos sooner than typical Ka regions. This is why the very first large objects are expected to be uncommon and biased towards special regions of the early density map. Over time, as more ordinary regions also grew, structure became more widespread. But the earliest giants likely began in the universe's rarest early high points. The first black holes may have formed from the collapse of massive early stars or from the direct collapse of gas, both influenced by early universe conditions. In one pathway, the first generations of stars could have been very massive, living short lives and collapsing into black holes at their ends. In another pathway, under certain conditions, large gas clouds might collapse so efficiently that they form a black hole without first fragmenting into many smaller B stars. Which pathway dominates depends on how easily the gas cools, how radiation affects it, and how the earliest halos assemble factors set by the young quote, universe's environment. These early black holes may then grow by accreting gas and merging, potentially becoming the seeds of the supermassive black holes seen in later galaxies. The Big Bang framework provides the timeline and conditions in which these earliest black holes could appear. The early phases of the Big Bang model involve particle interactions that depend on fundamental constants, making cosmology sensitive to particle B. Physics. Reaction rates, scattering strengths, and equilibrium conditions are governed by constants that determine how forces behave. In the early universe, these interactions happened everywhere, and small changes in interaction properties could, in principle, affect the expansion history, the AR. Formation of light elements, or the pattern in the CMB. This is one reason cosmology can constrain particle physics. The universe itself acted like an enormous high-energy experiment. Even when we can't reproduce those conditions on Earth, we can look for their lasting imprints in relic radiation and abundances. The early universe is therefore a quiet testing ground for the deep rules of physics. Measurements of primordial helium abundance provide an observational check on Big Bang nucleosynthesis predictions. Helium is produced both in the early universe and inside stars. So to test primordial predictions, scientists look for environments that are as chemically young as possible places with very low metallicity where stellar processing has been minimal. By estimating helium content in such regions and correcting for later stellar contributions, researchers infer a primordial helium fraction. This inferred value can then be compared to BBN calculations that depend on baryon density and early reaction rates. The broad agreement between predicted and observed primordial helium is an important consistency point for the Big Bang picture. It is a calm chemical echo from the universe's first minutes. Measurements of primordial deuterium abundance provide another check, often considered one of the cleanest because deuterium is easily destroyed in stars. Since deuterium tends to be burned away when gas cycles through stellar interiors, a high-quality primordial measurement typically focuses on distant, relatively pristine gas clouds. In such clouds, deuterium can remain close to its early universe value, making it an excellent test of BBN predictions. Deuterium is also highly sensitive to baryon density, so it provides a precise handle on how much ordinary matter existed early on. When deuterium-based baryon estimates agree with those inferred from the CMB, it strengthens confidence that the Big Bang model's early physics is consistent across independent evidence. This is why deuterium is treated like a particularly clear cosmic yardstick. The Big Bang model predicts a specific primordial helium-3 abundance, though interpretation is complicated because helium-3 can be produced and destroyed in stars. Helium-3 is not as straightforward as helium-4 because stellar processes can either increase or reduce helium-3 depending on the type of star. Its internal mixing. That means the helium-3 we measure today is not a pure fossil from the early universe. It is a mixture of primordial content and later stellar history. Still, the Big Bang model makes a baseline prediction that can guide expectations and be compared with carefully chosen observations. The complexity does not erase. The value it simply means helium-3 is a more delicate tracer than deuterium. It is another reminder that cosmological fossils can be altered by later astrophysical life cycles. The Big Bang model predicts lithium-7 production, but reconciling prediction and observation remains challenging. Lithium-7 is produced in small quantities during BBN, and the simplest calculations suggest a specific primordial amount. Yet when astronomers examine certain old metal-poor stars, often used as proxies for primordial composition, they sometimes infer less lithium than Tamda expected. This mismatch persists even with improved modeling, which is why it remains an active puzzle rather than a settled detail. Possible solutions range from lithium being depleted inside stars to more exotic changes in early universe physics. The lithium situation stands out because so many other BBN predictions match well. It is a quiet anomaly that keeps cosmologists careful and curious. The Big Bang model implies the universe had no center in the usual sense in homogeneous expansion. Space grows everywhere at once. In the simplest expanding universe description, every region sees other distant regions receding on average, not because everything is moving away from a tower, central point, but because the space between regions is stretching. This is similar to points on the surface of an inflating balloon. No point is the center of the surface's expansion, even though all points move away from each other along the surface. In three-dimensional cosmic expansion, the same idea applies in a more abstract way. The lack of a center is a geometric feature of the model, not a claim that the universe is featureless locally. It helps correct the common image of the Big Bang as a blast from one location. In an idealized Big Bang expansion, every observer sees distant galaxies moving away on average, with no special central point. This is a consequence of the cosmological principle. On large scales, the universe is roughly the same everywhere. If you place an observer in a distant galaxy, that observer also sees other galaxies receding, and they can measure their own version of Hubble's law. This symmetry means the expansion is not from us, and it is not toward us, but simply a property of the large-scale spacetime. Local motions still exist. Galaxies can move toward each other in groups, but the overall trend of distant recession is universal. It's a calm, democratic feature of expansion. No location gets special status. The Big Bang model does not require the universe to have begun from a single spatial point. It can describe a universe that was once uniformly dense, everywhere. In many cosmological solutions, if the universe is infinite today, it could also have been infinite in the past, just at a higher density. The beginning in such a description is not a point in space, but an early time when the density and temperature were extremely high throughout. This is another reason the phrase Big Bang can mislead, because it suggests a localized explosion. The model instead describes a global state of the entire universe, with expansion and cooling happening everywhere. This framing aligns better with the mathematics of standard cosmology. The term Big Bang was originally popularized in part as a critical label, yet it became the standard name for the hot expanding model. The phrase has a dramatic sound, which helped it stick in public imagination, even though the model itself does not describe an explosion in space. Over time, the term became widely used, and it now functions as the everyday name for the framework describing a hot, dense, early universe, followed by expansion. The historical origin is a small reminder that scientific terminology can start as rhetoric and later become conventional language. Even when the label is imperfect, the underlying model is defined by its predictions and evidence. The name remained, while the scientific content continued to sharpen. The Big Bang model implies that early universe processes set initial conditions that later influenced galaxy sizes, cluster distributions, and the scale of cosmic voids. Tiny differences in density and velocity in the early plasma became the seeds for gravitational growth. The statistical properties of those seeds, how strong they were on different scales, and how they were distributed, shape what structures form later. If the early fluctuations had been stronger, structure would have formed earlier, and more dramatically if weaker, structure would have been delayed. Features like the BAO scale also imprint preferred distances into later clustering. So the universe's large-scale pattern is not only a product of late-time gravity, but also a reflection of early initial conditions. The Big Bang framework connects those early conditions to the structure we map today. The Big Bang model predicts that early density fluctuations also lead to gravitational lensing effects that distort the shapes of distant galaxies. As matter clumps, it curves spacetime, and that curvature bends light passing through it. Over large distances, many small deflections add up, subtly stretching and shearing the images of background galaxies. This effect is called weak gravitational lensing because it is usually too small to produce dramatic arcs, yet it is strong enough to be measured statistically across millions of galaxies. The lensing pattern traces the distribution of total mass, including dark matter. In this way, the growth of structure seeded in the early universe creates a lensing fingerprint we can observe in the late universe. Weak gravitational lensing surveys use these distortions to map the distribution of dark matter. Because lensing responds to gravity, it does not care whether mass is luminous or invisible. By measuring the average shape distortions of many galaxies across the sky, scientists infer where mass is concentrated and how it is distributed on large scales. This provides a direct observational way to study dark matter's weeb-like structure, even though dark matter does not emit light. Lensing also helps measure how structures grow over time, because the amount of lensing depends on the clumpiness of matter along the line of sight. The method is subtle, requiring careful calibration of telescope effects and galaxy shape noise, but it is powerful. It turns faint distortions into a quiet map of the invisible universe. Combining lensing with CMB and BAO data provides cross-checks and tighter constraints on cosmological parameters. Each probe measures different aspects of the universe with different strengths and weaknesses. The CMB provides a clean, early-time snapshot, BAO provides a robust distance ruler at later times, and lensing provides a direct view of mass per hours, distribution, and growth. When these agree, confidence rises. When they differ, it highlights where new understanding may be needed. Combining them also reduces uncertainty because each probe breaks different parameter degeneracies. This is why modern cosmology often emphasizes joint analyses. Together, these methods form a calm network of evidence that reinforces the Big Bang model's quantitative structure. The Big Bang model predicts that the expansion rate at different epochs depends on the universe's component mix, which can be inferred by measuring distances versus redshift. Redshift gives you a way to tag cosmic time, while distance measures tell you how space has stretched between then and now. Different expansion histories driven by different amounts of matter, radiation, or dark energy produce different distance redshift relationships. By measuring many objects and features across a range of redshifts, cosmologists reconstruct how expansion changed over time. This is like building a timeline using multiple checkpoints. The more checkpoints we have, the more precisely we can describe the universe's expansion curve. BAO provides distance measurements, supernova provide relative distance measurements, and the CMB anchors early conditions. BAO gives a standard ruler length that can be compared across redshifts. Supernova provide a standardized brightness scale to infer distances, and the CMB sets the early universe baseline parameters that predict later behavior. Each probe covers different redshift ranges and different systematic uncertainties. When combined, they form a coherent expansion history that can reveal whether dark energy behaves like a cosmological constant or something more complex. The CMB's role as an early anchor is especially valuable because it ties late-time observations to well-understood early physics. This combination is one of the reasons the Big Bang framework feels so interconnected. Early relic light, late galaxy maps, and exploding stars all contribute to a single, consistent story. The Big Bang model predicts that the early universe had extremely high entropy in radiation, and expansion preserved a huge photon population. Entropy, in this context, is a measure related to how many microscopic configurations correspond to the large-scale state, and a hot radiation bath carries a great deal of it. The early universe was filled with photons and other relativistic particles in thermal equilibrium, producing a large entropy per comoving volume. As the universe expanded, the total number of photons in a given comoving region remained enormous, even as their energies fell. This helps explain why the CMB is such a pervasive background today. The photon population is not a minor left over, it is a dominant relic by number. Expansion cooled it, but it did not erase it. The uniformity of the CMB implies that early thermalization processes were efficient at establishing a common temperature field. For radiation to become so close to a perfect blackbody with near uniform temperature, matter and radiation must have exchanged energy effectively in the early dense phase. Frequent interactions allowed regions to share energy and approach equilibrium. This does not mean every point was identical, since small fluctuations remained, but it does suggest that large-scale equilibrium was established very core. Well, the result is a background radiation field that is astonishingly smooth. That smoothness is hard to obtain without a hot, interacting early state. So the CMB's uniformity is a calm sign of effective early thermal physics. The Big Bang model suggests that any pre-Big Bang or bouncer scenarios must reproduce its major observational successes: expansion, the CMB, and light element abundances. Alternative scenarios can be imaginative, but they have to match what the universe clearly shows us. The observed expansion history, the existence and blackbody nature of the CMB, and the primordial abundance pattern from BBN are not optional details. Any theory proposing a different beginning must still explain these results, at least as well as the Big Bang model does. That makes the Big Bang framework a benchmark. It sets constraints that alternatives must meet. In practice, matching the CMB's precise spectrum and anisotropy pattern is especially challenging. This is why many alternatives are judged by whether they can naturally reproduce these core successes. In many alternative scenarios, generating the observed CMB blackbody spectrum is a major hurdle. A blackbody spectrum implies a thermal origin with strong early interactions, and it remains blackbody shaped even after enormous expansion. Producing such a uniform, precise spectrum without a hot, dense phase is difficult because many non-thermal processes leave distortions. Even if a scenario can produce radiation, it must explain why the radiation is so evenly distributed and why its spectrum is so exact. This challenge is one reason the CMB is such a central pillar of Big Bang cosmology. It is not just the existence of background radiation, but the specific spectral shape that matters. The CMB's perfection is a calm but demanding constraint. The Big Bang model implies cosmological distances must be carefully defined because expansion changes how redshift, distance, and brightness relate. In everyday life, distance is straightforward, meters or kilometers between 2 points now. In cosmology, Distance depends on what you mean distance at emission time, distance now, or distance inferred from brightness. Expansion means that light travels through changing space. So simple Euclidean notions don't apply across billions of light years. This is why cosmologists define several distance measures that are each useful for particular observations. The model provides the mathematical framework for converting among these distances. Precision cosmology depends on choosing the right definition for the right measurement. Luminosity distance and angular diameter distance are two key ways to describe how objects appear in an expanding universe. Luminosity distance relates to brightness. It tells you how far away an object seems based on how dim it appears compared to its intrinsic luminosity. Angular diameter distance relates to apparent size. It tells you how far away something seems based on how big it looks in the sky compared to its true physical size. In an expanding universe, these two distances behave differently with redshift, even for the same object. They are connected through a known relationship, but they capture different observational aspects. Using the correct one is essential when interpreting supernova brightness or galaxy sizes at high redshift. In standard cosmology, angular diameter distance increases with redshift up to a point and then decreases, meaning very distant objects can appear larger in angular size than slightly nearer ones of the same physical size. This sounds surprising, but it comes from how expansion affects the geometry of light paths and the relation between emission time and observation time. At moderate redshifts, objects farther away look smaller, as expected. But beyond a certain redshift, you are looking back to a time when the universe was much smaller, and the geometry makes the angular size begin to increase again. So an object at very high redshift can, in principle, subtend a larger angle than an identical object at a somewhat lower redshift. This is not an optical illusion. It's a real geometric effect in expanding spacetime. It shows how cosmological intuition must be guided by the model's distance definitions. The Big Bang model predicts that time intervals for distant events appear stretched by a factor of 1 plus z, an effect called cosmological time dilation. If a process takes a certain time in the frame where it occurs, the expansion of the universe stretches the arrival times of its photons. That means the event appears to unfold more slowly when observed from far away, by a predictable amount tied to redshift. This is not because the distant physics is inherently slower, but because the expanding spacetime spreads out the time spacing of the signals we receive. This effect should apply to any time-varying phenomenon at cosmological distances. It is a clean prediction of expansion, connecting redshift not only to wavelength stretching, but also to time stretching. Observations of supernova light curves show time dilation consistent with expansion. Type Ia supernova rise and fall in brightness over a characteristic timescale, and when astronomers observe them at higher redshift, the light curves appear stretched out in time. The amount of stretching matches the expected 1 plus z factor within observational uncertainties. This supports the expanding universe interpretation and helps rule out alternative explanations for redshift that would not produce the same time effect. It is an elegant confirmation because it uses timing rather than spectral shifts. Supernova thus provide a calm and direct demonstration that cosmic redshift is tied to the expansion of spacetime itself. The Big Bang model implies that after certain epochs, photon number is largely conserved while photon energies redshift, producing the CMB's cooling. Once the universe becomes transparent and interactions that create or absorb large numbers of photons become rare, the total number of CMB photons in a comoving volume stays approximately fixed. But expansion still stretches their wavelengths, lowering their energies. That combination's stable photon count, falling energy per photon, means the radiation temperature drops smoothly over time, while preserving the blackbody. Spectrum shape. This is a key reason the CMB remains such a clean relic. The universe cools not by losing photons, but by gently reducing the energy of each photon through expansion. It's a quiet, geometric cooling mechanism. The Big Bang model predicts that early universe plasma oscillations leave an imprint that can be used to calibrate cosmic distances. Those oscillations set a physical scale link to the sound horizon that becomes a standard ruler. Because the physics of the early plasma is relatively well understood, this ruler can be predicted and measured in the CMB. Later, that same ruler shows up in BAO, allowing distances across cosmic time to be compared. This turns early universe microphysics into a practical measuring tool for the late universe. It is one of the most satisfying loops in cosmology. The early universe sets a scale, and the later universe displays it. By reading that imprint carefully, we learn how expansion proceeded. The standard cosmological model often assumes cold dark matter, meaning dark matter moved slowly compared to light during the era when structures formed. Cold here refers to low thermal speeds, not temperature in the everyday sense. If dark matter is cold, it can clump efficiently on small scales, helping small structures form early and merge into larger ones. This assumption matches many large-scale observations and is a cornerstone of the common lambdactum model. Cold, dark matter provides a natural way to build a hierarchical universe where small halos form first. It also helps reproduce the observed Weeb-like structure and galaxy clustering patterns. While the nature of dark matter is still unknown, cold describes the behavior that best fits many datasets. Cold dark matter naturally produces hierarchical structure formation, where small halos form first and merge into larger ones. In a cold dark matter universe, small-scale fluctuations survive and can collapse early, forming small gravitationally bound halos. Over time, these halos merge and accrete material, building bigger halos that host larger galaxies and clusters. This bottom-up growth is a central feature of many cosmological simulations and helps explain why galaxies show evidence of mergers and interactions. It also explains why structures exist across a wide range of sizes, from dwarf galaxies to massive clusters. Hierarchical growth is not chaotic randomness. It is an orderly outcome of gravity, acting on a cold, clump-friendly matter component. The universe builds complexity through repeated merging and growth. Warm dark matter models alter small-scale structure, and cosmological data can limit how warm dark matter could be. If dark matter particles move faster if they are warmer, they can smear out small-scale fluctuations by freeze streaming, preventing the smallest halos from forming easily. This would change the predicted number of small galaxies and the fine-grained structure of the cosmic web. Observations of galaxy distributions, lensing, and the matter-power spectrum can therefore constrain dark matter's warmth by showing how much small-scale structure exists. If we observe abundant small-scale clustering, that favors colder dark matter. If certain small-scale structures are missing, warm models become more plausible, though astrophysical effects can also complicate interpretation. In this way, cosmology helps narrow down what dark matter could behave like. The Big Bang model predicts that the early universe's density field should evolve into a specific large-scale correlation pattern, often described by the matter power spectrum. The matter-power spectrum is a mathematical way to describe how much structure exists at different scales, how bumpy the universe is when you look at different trees, sizes of regions. Its shape depends on initial fluctuations, the transition from radiation to matter domination, and the influence of dark matter and baryons. Over time, gravity transforms the initial spectrum into the present-day pattern of clustering. By measuring the power spectrum today and comparing it with predictions, scientists test whether the Big Bang model's evolution matches reality. It is a calm, statistical summary of the universe's structure, connecting the early density field to the later cosmic web. Galaxy surveys measure the matter power spectrum indirectly because galaxies trace underlying matter with some bias. Galaxies form in dense regions, so they are not perfect, unbiased traces of total mass. Some regions may have a lot of dark matter but fewer luminous galaxies, while others may be unusually efficient at forming stars. Because of this, the galaxy distribution is related to the matter distribution but not identical. Still, by mapping enormous numbers of galaxies, scientists can estimate the underlying clustering pattern, correcting for how galaxies populate halos. This makes galaxy surveys a key tool for probing the matter power spectrum on large scales. It is an indirect method, but with enough data and careful modeling, it becomes highly informative. The Big Bang model includes parameters describing bias, accounting for how luminous galaxies are distributed relative to total mass. Bias is a way of expressing the relationship between galaxy density fluctuations and matter density fluctuations. If bias is greater than 1, galaxies are more strongly clustered than matter, meaning they preferentially live in denser regions. Bias can depend on galaxy type, brightness, and redshift because different galaxies form under different conditions. In cosmological analyses, bias is modeled so that galaxy survey measurements can be translated into statements about total matter. Understanding bias is essential because it separates astrophysical formation details from the underlying gravitational structure. In this way, bias parameters let cosmologists use galaxies as tracers without pretending they are perfect mirrors of mass. The Big Bang model predicts that early radiation pressure prevented small-scale baryon clumping until after decoupling, influencing the timing of early star formation. Before recombination, baryons were coupled to photons, and photon pressure smoothed out small fluctuations, especially on smaller scales. That means ordinary matter could not easily collapse into dense clouds early on, even though dark matter could begin clumping. After decoupling, baryons were freed from that pressure and could begin falling into dark matter halos, but the delay influenced when the first dense gas clouds could fall. This affects the timing of the first stars and the pace of early galaxy formation. In other words, the early universe's pressure environment set a schedule for when baryonic structure could truly begin. It's a calm example of how light, once controlled, matter's ability to clump. The Big Bang model implies that the earliest galaxies likely formed in regions where dark matter halos reached sufficient mass to cool gas efficiently. A halo needs to be deep enough gravitationally to hold onto gas, and the gas needs a way to cool so it can collapse. In the earliest times, cooling channels were limited because heavy elements and dust were scarce. That means only halos above certain thresholds could gather gas dense enough to form stars reliably. Where those thresholds were met first, early galaxies could ignite. This creates a picture where early galaxy formation is uneven and biased toward particular environments and halo masses. The earliest luminous islands in the cosmos likely formed where gravity and cooling conditions quietly aligned. The Big Bang model predicts that the CMB should be statistically isotropic on large scales once we remove the dipole from our motion. Statistical isotropy means that the CMB's fluctuation properties should look the same in every direction when viewed in a broad, averaged sense. You can still have random hot and cold spots, but the overall statistical pattern should not prefer a particular direction. This expectation comes from the idea that the early universe was homogeneous and isotropic on large scales. After correcting for our motion relative to the CMB, scientists test whether the remaining pattern fits this isotropic expectation. This property is important because it supports the foundational assumption that the universe has no large-scale preferred direction. It is a calm symmetry check, built into modern cosmology. Tests for isotropy look for anomalies, alignments, or hemispherical differences, and these are studied carefully to distinguish real physics from statistical, quote, chance or observational effects. Because the CMB is a finite map with random fluctuations, it is always possible for unusual patterns to appear by chance. Additionally, measurement, issues like instrument noise, foreground contamination, or scanning patterns can introduce apparent asymmetries. Researchers therefore apply many tests. They compare one hemisphere to another, look for unusual alignments of large-scale features, and analyze whether results persist across different datasets. Some anomalies have been discussed, but interpreting them requires caution. The broader picture remains that the CMB is remarkably close to isotropic, which supports the standard model. These tests represent cosmology's careful habit, not just fitting a model, but checking its symmetries. The Big Bang model implies that the universe's expansion history can be reconstructed using multiple probes that overlap in redshift coverage. Different methods work best at different distances and times, so having overlapping ranges lets them cross-check each other. BAO provides standard ruler distances, supernova provides standardizable candle distances, lensing probes mass growth, and the CMB anchors early conditions. Because they overlap, scientists can compare whether a single expansion history fits them all. If it does, that supports the model. If not, it highlights where something may be missing. Reconstruction is therefore not a single measurement, but a tapestry of interlocking constraints. It is a calm, layered approach to building a timeline for how space has stretched. Cross-checking independent probes is crucial because each method has different systematic uncertainties. Supernova depend on calibration and dust corrections, BAO depends on survey selection and clustering modeling, and lensing depends on shape measurement and astrophysical contamination. The CMB has its own challenges, like separating foreground emission from the primordial signal. Because each probe has different vulnerabilities, agreement among them is especially convincing. Disagreement, meanwhile, can help identify which systematic effect might be responsible or whether new physics could be involved. This is why modern cosmology rarely rests on one kind of data alone. The Big Bang framework is strengthened by this calm redundancy across methods. The Big Bang model implies that early universe physics sets the sound horizon scale, which is then used for BAO distance calibration. The sound horizon depends on how fast sound waves traveled in the early photon baryon fluid and how long they had to travel before recombination ended. The oscillation era. That depends on baryon density, radiation content, and the expansion rate early on quantities constrained by the CMB. Once the sound horizon is known, it becomes a physical ruler imprinted on matter clustering. BAO observations then measure how that ruler appears at different redshifts, yielding distances and expansion information. In this way, early universe microphysics becomes a practical tool for late universe geometry. The ruler's origin is ancient, but its use is ongoing. Any new early universe physics that changes the sound horizon could shift inferred values of the Hubble constant from CMB and BAO analyses. Because CMB-based inferences of today's expansion rely partly on the calibrated sound horizon, changing that ruler length changes the derived Tamil distance scale. If the sound horizon was smaller or larger than assumed, the inferred Hubble constant could move in response. This is why some proposed solutions to the Hubble tension involve altering early universe conditions, adding extra radiation, or changing expansion briefly to adjust the sound horizon. Such changes must still fit the rest of the CMB and large-scale structure data, which is a strong constraint. The idea shows how interconnected the model is. Tweak an early ingredient, and late-time inferred numbers can shift. It is a calm demonstration of cosmology's internal consistency web. The Big Bang model predicts that the universe's matter content includes both visible baryons and invisible dark matter, with baryons being a minority by mass. Ordinary matter protons, neutrons, electrons make stars, gas, planets, and all familiar structures. But multiple lines of evidence show that the gravitational mass in the universe is far greater than what baryons alone can explain. In the standard picture, dark matter provides most of the matter mass, shaping structure formation and galaxy dynamics. Baryons then trace that structure by cooling and forming luminous objects within dark matter halos. This division is central. The universe's visible part is not the dominant mass component. The Big Bang framework integrates this by using both baryon and dark matter densities in expansion and structure calculations. Observations of galaxy rotation curves, gravitational lensing, and structure formation all support the existence of dark matter, which is integrated into BRATA, Big Bang cosmology. Rotation curves show that stars and galaxies orbit too fast to be held by visible matter alone, implying extra mass. Lensing reveals that light bends around clusters and galaxies more strongly than luminous matter can account for, mapping hidden mass distributions. Large-scale structure growth also fits better when most matter can clump early without radiation pressure, as dark matter would. These observations come from different scales and methods, yet they point toward the same conclusion. Additional non-luminous matter exists. The Big Bang model incorporates this by treating dark matter as a major matter component that influences both expansion and structure evolution. It becomes a quiet, necessary ingredient rather than an optional add-on. The Big Bang model predicts that ordinary matter is distributed not only in stars, but also in hot gas between galaxies, often described as the intergalactic medium. Most baryons are not locked inside shining stars. A large fraction exists as diffuse gas spread through space. Some of it is warm or hot, especially in and around galaxy groups and clusters, where gravitational heating and shocks raise temperatures. This gas can be difficult to see because it emits weakly and can be detected mainly through specific signatures like X-rays or absorption lines in the spectra of vague background objects. The presence of this diffuse baryonic component helps close the budget of ordinary matter predicted by cosmology. It also plays a major role in galaxy evolution because gas is the reservoir from which stars form and into which energy is returned. A significant fraction of baryons in the present-day universe resides outside stars in diffuse gas, and this fits well with cosmological accounting. When cosmologists infer how many baryons should exist from the CMB and from Big Bang nuclear synthesis, that number is larger than what you get by counting only the baryons locked into stars. The missing ordinary matter is not truly missing much of it. It's spread out in the space between galaxies as thin gas that can be warm, hot, or even very hot. Some of it is hard to detect because it does not shine brightly the way stars do, and it often reveals itself only through subtle absorption features or faint X-rays. Ray emissions. Over the last few decades, observations have steadily improved at tracing these diffuse baryons, especially in the intergalactic medium and the outskirts of our galaxy groups. This picture is comforting in a scientific sense because it means the baryon budget holds together across different methods and eras. The universe keeps its ordinary matter mostly in quiet, spread-out forms, rather than only in bright points of light. The Big Bang model implies that the earliest universe was more uniform than the universe is today, because structure growth increases contrast over time. Early on, density differences were tiny, just gentle ripples in an otherwise smooth cosmic fluid. As time passed, gravity slowly amplified these ripples, pulling matter into denser regions and leaving other regions emptier. This naturally increases contrast. Clusters become richer in matter, voids become more rarefied, and the overall pattern becomes more textured. The modern universe therefore looks clumpy, not because it began clumpy, but because it had a long time to develop clumpiness from subtle beginnings. This is one of the simplest and most satisfying narratives in cosmology. Small variations can grow into large structures if you give gravity enough time. The CMB shows the universe at a stage where the contrasts were still incredibly small, and galaxy surveys show the same system after billions of years of growth. It's a calm story of gradual development from near smoothness to rich complexity. The contrast between dense clusters and empty voids reflects billions of years of gravitational amplification. Galaxy clusters are like the universe's gathering places regions where gravity has pulled enormous amounts of matter together. Voids are the opposite, large regions where matter is scarce because it has been drawn away toward denser areas. This separation doesn't require an extra force beyond gravity. It arises naturally as matter flows down gravitational gradients. Over cosmic time, the process becomes self-reinforcing. Dense regions grow denser and better at attracting matter, while voids become emptier by comparison. Observationally, this contrast is one of the clearest visual signatures that the universe has been evolving for a long time. It is also a reminder that emptiness is not a failure of the cosmos, but part of its large-scale architecture. The web of clusters, filaments, and voids is the quiet end result of gravity patiently shaping initial ripples. The Big Bang model predicts that cosmic expansion affects not only light, but also the growth of structure through the changing expansion rate. Expansion and gravity interact. Gravity tries to pull matter together, while expansion stretches distances and can make collapse harder. If expansion is very rapid, matter has less time to gather before regions drift apart, so structure growth is slowed. If expansion is slower, gravity has more opportunity to amplify density differences, letting structures grow more efficiently. This means the universe's expansion history is not just a background setting, it actively influences how fast galaxies and clusters can form. That's why measuring expansion with supernova and BAO is directly relevant to understanding structure growth seen in lensing and galaxy clustering. Different components, radiation, matter, dark energy, change the expansion rate at different eras, and each era leaves its own signature in the growth of char. Structure. In a calm way, the universe's shape and its contents jointly decide how quickly the cosmic web becomes prominent. Faster expansion makes it harder for gravity to amplify structures quickly, while slower expansion gives gravity more time to grow clumps. You can picture gravity as a slow builder that works steadily, and expansion as a changing pace that can either help or hinder the builder's work. In the early radiation-dominated universe, expansion was fast and radiation pressure was strong, so growth of certain kinds of matter perturbations suppressed. Later, during matter domination, expansion slowed in the relevant sense, and gravity became more effective at building structure. At late times, if dark energy dominates and accelerates expansion, structure growth can slow again because the universe's stretching becomes more probable. Influential compared with gravitational gathering on large scales. This interplay is one reason cosmology often focuses on both geometry expansion and growth clustering. If you measure both, you can test whether the universe is behaving as the standard model predicts. It's a gentle balance. Gravity gathers, expansion stretches, and the universe's structure emerges from the competition. The Big Bang model implies that the cosmic age at a given redshift can be computed once cosmological parameters are specified. Redshift is not only a distance marker, it also corresponds to a time in cosmic history, because looking to high redshift means looking back to when the universe cars was smaller and younger. To translate redshift into age, you use the expansion history, which depends on the densities of matter, radiation, curvature, and dark energy. Once those parameters are measured, often from the CMB combined with other probes, the mapping from redshift to cosmic time becomes a well-defined calculation. This allows cosmologists to say things like, at redshift 6, the universe was less than 1 billion years old, with the exact number depending on the parameter set. It is a powerful way to place galaxies, reionization, and early star formation onto a single timeline. Instead of having scattered observations, you get a coherent chronological map. The universe becomes readable in time, as well as in space. In standard cosmology, a redshift of about 1 corresponds to a time when the universe was roughly half its present age, though the exact mapping depends on parameters. This is a useful rule of thumb that helps build intuition for cosmic time. Because the universe's expansion has not been uniform radiation dominated early, matter dominated later, and dark energy became important. More recently, the relationship between redshift and time is not linear. Still, around redshift 1, the universe was noticeably younger and the cosmic environment was different. Galaxies were generally more actively forming stars, and the overall matter density was higher. The half-age idea is not exact, but it captures that redshift 1 is not a slight step into the past, it's a substantial one. When astronomers observe objects around that redshift, they are seeing the universe at a significantly earlier stage of its development. This makes redshift a kind of cosmic clock hand, even if the tick marks depend on the universe's measured parameters. It's one more way the Big Bang model turns observations into a calm, ordered timeline. The Big Bang model predicts that the earliest chemistry was limited, because heavy elements and dust were absent until stars produced them. Chemistry as we know it, complex molecules, rocky minerals, and the building blocks of life requires elements heavier than helium. But the early universe began with mostly hydrogen and helium, plus trace light isotopes. That means the first gas clouds had fewer cooling pathways, because heavy elements and dust grains are very effective at helping gas lose heat. Without efficient cooling, gas tends to form stars in different ways, often favoring larger masses and more dramatic collapses. Only after the first generations of stars lived and died did the universe become enriched with carbon, oxygen, silicon, and other elements that enable richer chemistry. Dust grains formed from heavier elements also become important because they provide surfaces for molecules to form, and they affect how radiation moves through gas. So the universe's chemical complexity is an evolving story. First simple, then gradually enriched through stellar recycling. Dust formation later affected how starlight is absorbed and re-emitted, shaping galaxy observations and star formation processes. Dust is made of tiny solid particles, often silicates or carbon-rich grains created in the winds of evolved stars and in supernovae ejecta. Once dust exists in galaxies, it changes how we see them. Dust can absorb visible and ultraviolet light, making regions look dimmer or redder, and then re-emit that energy in infrared wavelengths. This means a galaxy can be actively forming stars while appearing less bright in visible light, because dust is hiding part of the activity. Dust also influences physics inside galaxies by helping gas cool, enabling denser cloud formation, and supporting molecule formation, including molecular hydrogen. In cosmology, Dust complicates observations but also provides a valuable signal when observed in the infrared. Its existence is a marker of chemical enrichment and stellar processing over time. In a quiet way, dust is both a veil and a storyteller. It hides some light while revealing a galaxy's maturity and history through its own emission. The Big Bang model's early hot phase means the universe once emitted intense high-energy radiation, though that radiation has since been stretched into microwaves. In the early universe, the temperature was high enough that the typical photon energies were far greater than microwave energies. At sufficiently early times, the background radiation would have been in the visible or ultraviolet range, and earlier still, it would have been even more energetic. But as the universe expanded, those photon wavelengths stretched, lowering their energies in a steady, predictable way. Over billions of years, this cooling shifted the background radiation into the microwave band we measure today as the CMB. So the microwave background is not a separate phenomenon from the early heated, is the cooled form of that early radiation field. This helps connect a quiet modern measurement of faint microwave glow to a much hotter and more energetic ancient universe. It's a gentle reminder that expansion not only moves things apart, but also transforms the energy character of the cosmos over time. The Big Bang model predicts that the CMB should be observable from all directions, and Forsky measurements show exactly that. Because the CMB is a relic from a time when the universe became transparent, and because that event occurred everywhere, we expect to see the afterglow coming, quote, toward us from every line of sight. This does not mean photons are arriving from the same physical location. It means that in every direction there is a surface of last scattering at a great distance where the photons last interacted strongly with matter. Satellites and ground-based experiments have mapped the CMB across the sky, confirming its near-uniform presence and its tiny anisotropies. The fact that it fills the entire sky is a key reason it is treated as a cosmic background rather than a localized astrophysical source. It is one of the most direct observational supports for a hot, dense early phase, followed by expansion and cooling. The sky itself, in every direction, carries the same quiet signature. Satellite missions were crucial for measuring the CMB cleanly, because Earth's atmosphere emits and absorbs microwaves that interfere with observations. The atmosphere is not transparent at all microwave frequencies, and it also produces its own microwave emission, which can swamp the faint cosmic signal. While ground-based and balloon experiments can do excellent work in certain frequency bands and locations, satellites avoid many of these limitations by observing above the atmosphere. This allows more stable coverage, cleaner measurements, and often the ability to map the entire sky. Satellite missions also reduce certain systematic issues that arise from looking through varying atmospheric conditions. The result has been a progression from discovery to precision, from detecting the CMB at all to measuring its spectrum with extraordinary accuracy, to mapping its anisotropies and polarization in detail. These measurements are part of why cosmology now has such tight parameter constraints. The quiet background glow became one of the most precisely measured signals in all of science. Improvements in CMB observations over time allowed measurement not just of the CMB's existence, but of its fine anisotropy structure. Early measurements established that the CMB was there and roughly uniform. Later, more sensitive instruments detected tiny temperature variations across the sky, revealing the pattern of primordial fluctuations. As resolution and sensitivity improved, the acoustic peak structure in the power spectrum became sharply defined, enabling precise estimates of cosmological parameters. Polarization measurements then added another layer, refining constraints and testing additional physics like reionization history and lensing. Each improvement turned the CMB from a simple, yes it exists discovery, into a detailed early universe map. This is why the CMB is often described as a treasure trove. It is one signal with many encoded stories. Over time, careful measurement has slowly unfolded those stories. The Big Bang model implies that early universe conditions can often be described statistically rather than by tracking individual particles. Because large scale behavior depends on averaged quantities. The early universe contained enormous numbers of particles interacting frequently, which makes it impractical and unnecessary to follow each one. Instead, cosmology uses concepts like temperature, density, pressure, and small perturbations in those quantities. These averaged descriptions capture the overall behavior of the system with high accuracy, because the universe was close to thermal equilibrium on large scales. Statistical descriptions also match how the CMB and large-scale structure are observed. We measure patterns and correlations, not individual particle histories. This approach is one reason cosmology can be both simple and powerful, simple in its macroscopic variables, powerful in its predictions. Even when the underlying microphysics is complex, the large-scale outcome can be described with calm statistical clarity. The Big Bang model uses perturbation theory to connect tiny early fluctuations to the patterns we see in the CMB and large-scale structure. Perturbation theory is a method for handling small deviations from a simple background solution. The background universe is treated as smooth and expanding, and then small fluctuations like the tiny density differences seen in the CMB are added as keen perturbations. Because these perturbations are small at early times, their evolution can often be calculated with controlled approximations, producing predictions for how their statistical properties should appear in the CMB power spectrum and in the matter power spectrum. Over time, some perturbations become large and nonlinear, especially in galaxy formation, but many large-scale features remain well described by the AI. The turbative approach. This method bridges the early and late universe in a mathematically grounded way. It's a calm technique that turns tiny ripples into a predictive framework for cosmic structure. The Big Bang model predicts that gravitational potentials in the early universe influenced photon paths, contributing to anisotropies through gravitational path, redshift, and lensing. When photons travel through regions of different gravitational potential, their energies can shift and their paths can bend slightly. At last, scattering. Photons emerging from deeper potential wells lose energy climbing out, appearing slightly cooler, while photons from shallower regions appear warmer. This is part of the Sachs-Wolf effect. As photons travel across billions of years, they also pass through later formed structures that lens them, subtly distorting the CMB's pattern. These effects mean the CMB is both a snapshot and a journey record. It carries information from its birth environment and from what it encountered along the way. Measuring these influences helps cosmologists infer the distribution of matter, including dark matter, and refine constraints on parameters like neutrino masses. It is quiet evidence that gravity imprints itself on light in multiple stages. The universe's large-scale gravitational landscape becomes visible through its gentle influence on ancient photons. The Big Bang model implies that cosmic expansion can be parameterized by the scale factor, AT, a central function in cosmological calculations. The scale factor is a simple way to describe how the size of the universe changes with time in a homogeneous model. If the scale factor doubles, distances between faraway moving points double. By defining AT, cosmologists can express redshift, density scaling, horizon growth, and many other relationships cleanly. It turns the expansion history into a single mathematical function that can be derived from the Friedmann equations given the universe's energy components. In practice, AT is not measured directly like a ruler, but inferred from observations like supernova distances, BAO, and the CMB. This makes the scale factor a quiet backbone of cosmological reasoning. It allows a consistent description of how the universe transitioned from hot and dense to cool and expanded. The scale factor is commonly set to 1 today, with smaller values representing earlier times. This is a convenient normalization. It means all other scale factor values are relative to the present. If AT was 0, 5 at some time, that means the universe's linear scale was half what it is now, and redshift at that time would be related to that ratio. This convention makes equations simpler and comparisons easier. It also emphasizes that size in cosmology is relative, not absolute in the everyday sense, because the universe can be infinite and still have a meaningful scale factor describing relative expansion. By tying AT to redshift through 1 plus Z equals 1/A in that normalization, cosmology gets a clean translation between observational redshift and theoretical expansion. It's a calm, organizational choice that makes the whole framework more readable. The Big Bang model implies that the mean density of matter scales roughly as AT3 as the universe expands, because matter is diluted by increasing volume. If you imagine a fixed number of matter particles in a comoving region, and space expands so that lengths scale with AT, then volume scales with AT3. With the same amount of matter spread over a larger volume, density falls as 1 over the volume, giving the A3 scaling. This is why matter density was much higher in the past when the universe was smaller. It also helps explain why the expansion rate changed. Higher density means stronger gravitational influence in the Friedmann equations. This scaling is simple, but it is one of the core reasons cosmology can compute how different eras unfold. Matter thins out steadily as the universe grows. The energy density of radiation scales roughly as AT because radiation is diluted by volume and each photon loses energy to redshift. Radiation density falls faster than matter density because there are two effects at once. First, just like matter, photons spread out as volume increases, giving an A3 dilution. Second, each photon's energy decreases because its wavelength is stretched by expansion, adding another factor of A. Multiply these together and you get her. This is why radiation dominated early. When AT was small, A was huge compared to a 3, so radiation energy density outweighed matter. As expansion proceeded, radiation faded faster, allowing matter to take over. This scaling is a quiet mathematical reason behind the universe's changing eras. If dark energy is a cosmological constant, its energy density stays roughly constant as the universe expands. Unlike matter and radiation, a cosmological constant does not dilute with volume in the same way. In that model, the energy density of dark energy remains approximately the same, even as space grows. So the total amount of dark energy in a larger region increases with volume. This property is one reason a cosmological constant can drive accelerated expansion. As matter thins out, the constant component eventually dominates. This doesn't mean dark energy behaves like ordinary stuff. It's more like a property of space-time itself, in the simplest interpretation. Its constancy makes the late universe very different from the early universe. It is also why dark energy becomes influential only after the universe has expanded enough that matter density has fallen substantially. This differing scaling behavior explains why dark energy becomes more influential at late times in such models. Early on, matter and radiation densities were enormous, so a constant dark energy density was relatively insignificant. But as expansion continued, matter diluted as a 3 and radiation as A, steadily shrinking their contribution to the total energy budget. Meanwhile, a constant dark energy density stayed the same, so its fractional share grew. Eventually, dark energy became the dominant term, changing the expansion from decelerating under matter's gravity to accelerating under dark energy's influence. This is a gentle, inevitable crossover. If a cosmological constant is present, the faster diluting components fade, leaving the constant one behind. It's an elegant example of how simple scaling laws can predict major transitions in cosmic history. The late-time universe's acceleration is, in this view, a natural outcome of how different components scale. Many open questions remain, like the nature of dark matter, the origin of the matter-antimatter asymmetry, and the physics of the earliest instance. But they are studied within the Big Bang cosmological picture. The Big Bang model is not a claim that every detail is solved. It is a framework that successfully links many observations while leaving room for deeper mysteries. Dark matter remains unidentified in particle terms, even though its gravitational role is strongly supported. Baryogenesis remains an open puzzle about why matter dominates over antimatter. The earliest instance, where quantum gravity may matter, remain beyond complete description. Yet these questions are not disconnected from the model. They are motivated by it and constrained by it, because any new answers must still fit the CMB, expansion history, and light element abundances. In that sense, the Big Bang framework acts like a calm, sturdy stage on which the remaining mysteries are explored. It provides a coherent story for the universe's evolution while inviting continued discovery at its deepest edges. May you rest easily tonight and drift into sleep with the quiet thought that the universe has been expanding, cooling, and unfolding its structure with patient valor. Steadiness for a very long time.